There's something lurking in the vastness of space, something that defies the way we classify stars and planets. Too massive to be a planet, but too small to be a star, these mysterious objects drift in the darkness, hidden between the glowing beacons of the universe. Scientists call them brown dwarfs, but the truth is, we still don't fully understand them. They're cold, faint, and nearly impossible to see with the naked eye. Yet they might hold the key to unlocking some of the greatest mysteries of space. What are they? How do they form? And could they be the missing link between planets and stars? To understand brown dwarfs, we have to start with how stars are born. In the vast clouds of dust and gas scattered across galaxies, gravity pulls material together. If enough mass accumulates, pressure and temperature rise, eventually igniting nuclear fusion, the process that makes stars shine. But sometimes things don't go as planned. Sometimes, an object starts forming like a star but doesn't gain enough mass to sustain fusion. Instead of becoming a glowing ball of plasma, it fizzles out before it ever truly begins. This is a brown dwarf. Unlike normal stars, brown dwarfs never reach the temperature needed to fuse hydrogen into helium. This means they don't burn bright like our sun, and instead, they glow faintly with leftover heat from their formation. Some brown dwarfs can fuse a heavier form of hydrogen called deuterium, but only for a short period before that energy runs out. Without fusion, they cool over time, becoming even harder to detect. For decades, brown dwarfs were just a theory. Scientists predicted their existence, but because they emit so little light, they remained hidden. It wasn't until 1995 that astronomers finally confirmed the first brown dwarf. Since then, thousands more have been discovered, yet we still don't fully understand them. Some are floating alone in space, while others orbit stars like giant planets. And some challenge everything we thought we knew about how objects form in the universe. What makes brown dwarfs so fascinating is that they blur the line between stars and planets. Some are only a little bigger than Jupiter, yet they formed like stars instead of planets. Others are much larger, but they lack the mass needed to shine. Because of this, scientists often call them failed stars. But that label doesn't quite capture how unique they are. They may not be stars, but they're not planets either. They exist in their own strange category, one that might reveal secrets about the formation of solar systems, the structure of exoplanets, and even the hidden population of rogue objects drifting through space. Detecting brown dwarfs is no easy task. Since they don't shine brightly, they're nearly invisible to regular telescopes. Instead, astronomers use infrared observations to find them. Unlike stars, which emit most of their energy in visible light, brown dwarfs glow mainly in infrared, essentially giving off heat instead of bright light. This means we need special instruments to see them, like NASA's Spitzer Space Telescope and the James Webb Space Telescope, which can peer deep into space using infrared technology. One of the biggest questions about brown dwarfs is how they form. Do they form like stars, collapsing from giant clouds of gas? Or do they form like planets, growing from a disk of material around a larger star? The answer isn't entirely clear. Some brown dwarfs appear alone in space, suggesting they formed like small stars. Others are found in planetary systems, hinting that they may have formed like gas giants. The distinction matters because it could change our understanding of planet formation. If some planets are actually failed stars, then where do we draw the line between the two? Another mystery surrounding brown dwarfs is their atmosphere. Unlike stars, which have blazing hot surfaces, brown dwarfs have cooler, more complex atmospheres with strange weather patterns. Some have thick clouds of iron and silicate dust, creating bizarre storms. Others have swirling bands of gas, similar to Jupiter but on a much larger scale. Studying these atmospheres could give us insight into exoplanets, especially gas giants that orbit distant stars. Since brown dwarfs and giant planets share many characteristics, understanding one could help us understand the other. But perhaps the most exciting possibility is that brown dwarfs could host moons or even habitable environments. While they don't produce much heat, some brown dwarfs are warm enough to keep a planet or moon at a stable temperature. If a rocky moon orbits close enough, it might be warm enough for liquid water, a key ingredient for life as we know it. This raises the question, could life exist around a brown dwarf? While it's unlikely in the traditional sense, it's not impossible. Some scientists believe that under the right conditions, life could adapt to the dim glow of a brown dwarf, much like deep-sea creatures on Earth survive in total darkness. Then there's the question of rogue brown dwarfs, those that wander the galaxy without a home. Unlike stars, which are often bound to galaxies, brown dwarfs can drift freely through space. Some may have been ejected from star systems, while others formed in isolation. These rogue objects are fascinating because they could be some of the most common celestial bodies in the universe. Yet, because they're so hard to detect, we've only found a fraction of them. Some scientists speculate that billions of these objects could be lurking in the darkness, hidden between the stars. As we continue to study brown dwarfs, new discoveries keep changing what we think we know. Some brown dwarfs challenge our definitions of what a planet is, while others raise questions about how stars form. With new telescopes and better technology, we may soon uncover even more mysteries hidden within these strange, in-between objects. But for now, they remain one of the most intriguing enigmas of space, neither star nor planet, but something entirely unique. And the more we learn about them, the more we realize how little we truly understand about the universe. Brown dwarfs don't just challenge our understanding of stars and planets, they force us to rethink what's even possible in the universe. For decades, we assumed that celestial bodies fit into neat categories: stars that shine, planets that orbit, and everything in between was either too small or too insignificant to matter. But brown dwarfs prove that nature doesn't follow our rules. They exist in a gray area where definitions blur, where failed stars and oversized planets become nearly indistinguishable. And as we uncover more about them, we realize they might not be as rare as we once thought. One of the most mind-blowing discoveries about brown dwarfs is that they come in an incredible range of sizes, temperatures, and compositions. Some are just barely more massive than Jupiter, while others approach the lower limit of true stars. Some glow with a faint reddish hue, while others are so cold they could pass for giant planets. The coldest brown dwarfs we've found, known as white dwarfs, have temperatures barely above freezing. In fact, some are cooler than a cup of coffee. Imagine that, a failed star drifting through space, with temperatures low enough that ice could exist on its surface. But the variety of brown dwarfs doesn't stop at temperature. Their atmospheres are just as diverse as their sizes. Unlike stars, which have relatively uniform outer layers, brown dwarfs have dynamic, chaotic weather systems. Some have thick clouds of silicates, which means that, instead of water vapor like on Earth, their skies could be filled with molten rock. Others have massive storms that make Jupiter's great red spot look tiny in comparison. These storms can cover entire hemispheres, with winds that rage at thousands of kilometers per hour. Imagine standing on a world where the sky rains molten iron, and clouds of vaporized metal swirl in a violent, endless storm. That's the reality of some brown dwarfs. But what's even stranger is that some brown dwarfs seem to have seasons. On Earth, seasons are caused by the tilt of our planet as it orbits the Sun. But brown dwarfs don't orbit stars, they drift through space alone. So why would they have seasons? The answer lies in their atmospheres. As a brown dwarf cools, different elements condense at different heights, creating shifting cloud layers. This means that over time, the appearance of a brown dwarf can change dramatically. A telescope looking at the same brown dwarf over months or years might see completely different cloud patterns, as if the object were going through its own bizarre version of summer and winter. Another mystery surrounding brown dwarfs is their magnetic fields. Despite their small size, some brown dwarfs have incredibly powerful magnetic fields, even stronger than those of many stars. This leads to something unexpected. Brown dwarfs can produce auroras, just like planets. Normally, auroras happen when charged particles from the Sun interact with a planet's magnetic field. But brown dwarfs don't have a star bombarding them with solar wind, so where do these charged particles come from? The answer isn't entirely clear, but some scientists suspect that brown dwarfs generate their own particles through processes deep inside their atmospheres. Others think they might have hidden companions, unseen planets, or moons that provide the energy needed to spark these glowing displays. Either way, the fact that some brown dwarfs light up with brilliant auroras is yet another example of how strange and unexpected these objects really are. And then there's the question of how common brown dwarfs really are. For a long time, they were thought to be rare, but new discoveries suggest they might be one of the most abundant objects in the universe. Because they're so faint, many have gone undetected. But with infrared telescopes scanning deeper into space, we're finding more of them all the time. Some astronomers now believe that for every few stars in the galaxy, there could be at least one brown dwarf lurking nearby. If that's true, then brown dwarfs could outnumber many types of stars, making them a major but hidden component of the universe. But even more intriguing is the idea that some brown dwarfs might not have formed like stars at all. Traditionally, we think of brown dwarfs as failed stars, objects that started forming in a gas cloud but never gained enough mass to ignite fusion. But what if some brown dwarfs are actually super-sized planets that got ejected from their home systems? In chaotic young solar systems, it's common for massive planets to be thrown out due to gravitational interactions. If a gas giant like Jupiter were to be flung into interstellar space, it would look almost exactly like a brown dwarf. This means that some of the brown dwarfs we found might not be failed stars, but instead orphan planets, cast away from their home systems and left to wander the galaxy alone. This raises another fascinating question: what if some brown dwarfs have planetary systems of their own? We usually think of planets as orbiting stars, but there's no rule saying they have to. If a brown dwarf is large enough, it could have a system of moons or even smaller planets orbiting around it. And if one of those planets were at the right distance, it might even have conditions that support life. While a brown dwarf wouldn't provide the same warmth and light as a star, its residual heat might be enough to keep a planet's surface warm. And if that planet had a thick atmosphere or active geology, it could trap enough heat to sustain liquid water. Could life exist in such a system? It's a long shot, but not impossible. After all, on Earth, we've found life in some of the most extreme conditions imaginable: boiling hot hydrothermal vents, frozen Antarctic lakes, and deep underground. If life can thrive in those environments, who's to say it couldn't survive around a brown dwarf? Perhaps the biggest mystery about brown dwarfs is what happens to them over billions of years. Unlike stars, which eventually explode or fade into white dwarfs, brown dwarfs don't have a clear end point. They don't burn through fuel, and they don't collapse into black holes. Instead, they just cool and dim over time, gradually fading into the darkness. But what does a brown dwarf look like after trillions of years? Do they become completely invisible, radiating only the faintest whispers of heat? Or do they eventually stabilize at some final, ultra-cold state? Since the universe itself isn't old enough to have fully cooled brown dwarfs, we don't yet know the answer. But if brown dwarfs truly never die in the same way stars do, then they could be among the longest-lived objects in the universe. Silent remnants of the past, drifting endlessly through space long after normal stars have burned out. Brown dwarfs remain one of the greatest space mysteries. They defy easy categorization, blending the characteristics of planets and stars in ways we never expected. They challenge our definitions, hint at unseen forces, and may even play a crucial role in shaping planetary systems. The more we study them, the more we realize how little we truly know. And perhaps that's the most exciting part, because with every new discovery, we're not just uncovering the secrets of brown dwarfs, but the secrets of the universe itself. Brown dwarfs are more than just cosmic misfits. They are a window into the hidden mechanics of the universe. These strange objects challenge our understanding of how celestial bodies form, evolve, and interact with their surroundings. And the more we study them, the more we realize that they may hold the key to answering some of the most fundamental questions in astronomy. One of the most puzzling things about brown dwarfs is their formation. Traditionally, we categorize star formation as a process where gas and dust collapse under gravity, heating up until nuclear fusion ignites in the core. Planets, on the other hand, are thought to form in the disks of material surrounding young stars, gradually accumulating mass over time. But brown dwarfs don't fit neatly into either of these categories. Are they failed stars that never gathered enough mass? Or are they supersized planets that formed independently in space? The answer might be both. Some brown dwarfs seem to form in ways similar to stars, condensing from clouds of gas in interstellar space. But others might form like giant planets and later get ejected from their home systems, wandering alone in the darkness. If that's the case, then the distinction between planets and brown dwarfs isn't as clear-cut as we once thought. It's entirely possible that many of the objects we call brown dwarfs today were once part of planetary systems, thrown into the void through chaotic gravitational interactions. And that leads to another mystery. How many brown dwarfs are out there, drifting unseen between the stars? For years, astronomers struggled to detect brown dwarfs because they emit so little visible light. Unlike stars, which shine brightly due to nuclear fusion, brown dwarfs only glow faintly from leftover heat. This means that traditional telescopes, which rely on visible light, often miss them entirely. But with the advent of infrared astronomy, we've started to uncover just how many of these objects are lurking in the darkness. Recent surveys suggest that brown dwarfs might be far more common than we ever imagined. Some scientists believe that for every few stars in the Milky Way, there could be at least one brown dwarf hiding nearby. That means our galaxy alone might contain billions, if not trillions, of these strange objects. And if they're this common in our galaxy, it stands to reason that they're just as common elsewhere in the universe. This raises the possibility that brown dwarfs could be one of the most numerous celestial objects, filling the vast spaces between stars with their faint, ghostly glow. But even more intriguing is the idea that brown dwarfs might be able to host planetary systems of their own. Normally, we think of planets as orbiting stars, but there's no reason they couldn't orbit brown dwarfs as well. In fact, some brown dwarfs have been found with planetary companions, suggesting that entire systems might exist around these failed stars. And if that's true, it opens up the possibility that some of these planets could harbor conditions suitable for life. Of course, living around a brown dwarf would be very different from living around a star. Because brown dwarfs don't produce much visible light, any planets orbiting them would exist in a dim, twilight-like environment. But that doesn't necessarily mean life couldn't exist. Some brown dwarfs still emit enough heat to warm nearby planets, and if a planet had a thick enough atmosphere, it could trap and retain that heat, creating a stable climate. In fact, some scientists have speculated that life could even evolve in subsurface oceans on these planets, much like we see with the icy moons in our own solar system. But the mystery of brown dwarfs doesn't stop there. Some of them exhibit behavior that seems almost impossible for objects of their size. One of the most surprising discoveries in recent years is that some brown dwarfs produce powerful radio emissions, similar to those seen in planets with strong magnetic fields. In fact, some brown dwarfs generate radio signals that are even more intense than those of massive planets like Jupiter. This suggests that they have extremely strong magnetic fields, but why? Normally, a planet's magnetic field is generated by a molten metal core that rotates and produces electric currents. But brown dwarfs are much larger than planets, and they don't have solid cores like Earth or Jupiter. So where do these magnetic fields come from? Some scientists believe that the interiors of brown dwarfs might be in a state of constant motion, with massive currents of electrically charged gas generating these powerful fields. Others suggest that interactions with unseen companion objects, perhaps planets or smaller brown dwarfs, could be amplifying their magnetic activity. Whatever the cause, the fact that brown dwarfs can produce such intense radio emissions challenges our understanding of how magnetic fields work in the universe. It also raises the question of what else these objects might be capable of. If some brown dwarfs have strong magnetic fields, could they also produce auroras? The answer appears to be yes. In fact, some brown dwarfs have been observed with bright auroras glowing in their atmospheres, just like we see on Earth and Jupiter. But unlike planets, which rely on the solar wind to fuel their auroras, brown dwarfs don't orbit a star. So where do these charged particles come from? One possibility is that some brown dwarfs have their own internal mechanisms for generating charged particles. Another idea is that they might have unseen companions, perhaps small planets or moons, that interact with their magnetic fields in a way similar to how Jupiter's moon Io fuels its auroras. But without a clear explanation, the presence of auroras on brown dwarfs remains one of the biggest unanswered questions in astronomy. And then there's the biggest mystery of all: what happens to brown dwarfs over time? Unlike stars, which burn through their fuel and eventually die in spectacular explosions or fade into white dwarfs, brown dwarfs don't have a clear end state. They don't undergo nuclear fusion, so they don't experience the same life cycle as stars. Instead, they simply cool and dim over billions or even trillions of years. But what does a brown dwarf look like after an unimaginable amount of time has passed? Do they eventually become completely dark, radiating only the faintest traces of heat? Or do they stabilize at some final, ultra-cold state? Since the universe itself isn't old enough for any brown dwarfs to have reached this final stage, we don't yet know the answer. But if brown dwarfs truly never die in the traditional sense, then they could be some of the longest-lived objects in the cosmos, drifting silently through space for eternity. Brown dwarfs remain one of the greatest space mysteries. They defy easy categorization, blurring the lines between stars and planets in ways that challenge our understanding of astrophysics. They may be more common than we ever imagined, hidden in the vast darkness of interstellar space. They might host their own planetary systems, complete with moons and even the possibility of life. They produce strange radio signals, powerful magnetic fields, and glowing auroras, raising questions about what other surprises they might hold. And as we continue to study them, they may force us to rethink not just how stars and planets form, but the very nature of the universe itself. Brown dwarfs might not shine as brightly as stars, but their significance in the universe cannot be overstated. They challenge the traditional boundaries between celestial objects, raising questions about what truly defines a star, a planet, or even something in between. The more we study them, the more we realize how much we still don't know. And perhaps the biggest mystery of all is just how many of them are lurking unseen in the depths of space. One of the key reasons brown dwarfs remain so elusive is their temperature. While stars burn with intense heat, brown dwarfs only glow faintly, and their temperatures can vary dramatically depending on their age. The youngest brown dwarfs are still warm from their formation, sometimes reaching thousands of degrees, but over time, they cool down. The coldest known brown dwarfs have surface temperatures barely above room temperature, making them nearly indistinguishable from rogue planets, or even giant gas planets like Jupiter. This cooling process makes them increasingly difficult to detect, especially as they age and fade into the background of space. In recent years, astronomers have made significant progress in finding brown dwarfs by using infrared telescopes. Infrared light is key to detecting objects that are too cool to shine brightly in visible light. The Wide Field Infrared Survey Explorer, WISE, has been instrumental in identifying new brown dwarfs, including some of the coldest ever found. Some of these objects, known as white dwarfs, have temperatures as low as 80 degrees Fahrenheit, about 27 degrees Celsius, meaning they could theoretically feel warm to the touch if you could stand on them. This discovery has led to an even more fascinating question: are there even colder, darker objects out there? Some scientists speculate that there may be brown dwarfs so cold that they are practically indistinguishable from large gas planets, making them nearly impossible to detect. If such objects exist, they could be drifting in the vast emptiness of interstellar space, completely invisible to our current technology. Some have even suggested the possibility of black dwarfs, brown dwarfs that have cooled to the point where they emit almost no detectable radiation. If these ultra-cool brown dwarfs are out there, how many could there be? The answer could change our entire understanding of the structure of the galaxy. If brown dwarfs vastly outnumber stars, it could mean that much of the mass of our galaxy is hidden in these cold, dark objects. And if they are this common, it raises another question: could some of them be relatively close to us without us even knowing? One of the most exciting discoveries in brown dwarf research was the realization that some of them are among the closest objects to our solar system. In fact, the closest known system beyond the Alpha Centauri star system is a pair of brown dwarfs known as Lumen 16, located just 6.5 light-years away. This means that brown dwarfs are not just distant objects in other galaxies. They are right here, in our cosmic backyard. But why does this matter? Because if brown dwarfs are common near us, then they are likely common everywhere. And if we haven't even detected all the ones in our own neighborhood, What does that say about the number that might exist throughout the Milky Way and beyond? Could brown dwarfs actually be more numerous than stars, making up a vast, hidden population of failed suns? If so, then brown dwarfs might play a much bigger role in the overall structure of the universe than we ever imagined. Some astronomers have even speculated that brown dwarfs could be a significant contributor to dark matter, the mysterious, invisible substance that makes up most of the mass in the universe. While brown dwarfs alone are unlikely to account for all of dark matter, the possibility that they contribute to the hidden mass of galaxies is an intriguing idea that deserves further study. Another question that remains unanswered is how brown dwarfs behave over time. Because they don't undergo traditional stellar evolution, they don't explode as supernovae or collapse into black holes like massive stars do. Instead, they simply cool and fade, potentially lasting for trillions of years. This makes them some of the most stable objects in the universe. But what happens to them at the end of their life cycle? If brown dwarfs truly never die in the traditional sense, then they could remain as dim, barely detectable objects for an eternity. Over vast cosmic timescales, as stars burn out and galaxies evolve, could brown dwarfs eventually become the dominant objects in the universe? Could they outlast everything else, surviving long after all the stars have died? This leads to one of the most mind-bending possibilities. The idea that in the far, far future, long after the last stars have burned out, brown dwarfs could be among the last sources of heat and energy in a dying universe. As the cosmos continues to expand and cool, brown dwarfs might be the last warm objects left, slowly radiating away their final traces of heat into an increasingly empty void. And what if some of them are not alone? If brown dwarfs have planetary systems, then their planets could remain orbiting them for unfathomable periods of time. Some of these planets might have subsurface oceans kept warm by residual heat, potentially allowing for life to exist in conditions completely different from what we know. Could it be that the last remnants of life in the universe will one day exist on a distant, icy moon orbiting a long-cooled brown dwarf, billions of years after all the stars have vanished? The more we learn about brown dwarfs, the more we realize how much we don't know. They challenge our definitions, defy our expectations, and hint at secrets we have yet to uncover. They could hold the key to understanding planetary formation, galactic evolution, and even the fate of the universe itself. As new telescopes and technologies continue to improve our ability to detect and study them, we may one day unlock even deeper mysteries hidden within these strange, failed stars. But for now, brown dwarfs remain one of the greatest enigmas of the cosmos, silent wanderers, drifting through the darkness, waiting to reveal their secrets to those who dare to look. Brown dwarfs, often described as failed stars, challenge our understanding of celestial bodies. They exist in a strange limbo between planets and stars, either massive enough to sustain hydrogen fusion like the Sun, nor small enough to fit neatly into the category of gas giants like Jupiter. But their existence raises profound questions. How many are there? Could they be more common than we think? And what role do they play in shaping the structure of the universe? One of the most intriguing aspects of brown dwarfs is how they form. Traditional star formation begins with a dense cloud of gas collapsing under its own gravity, heating up and eventually triggering nuclear fusion. But brown dwarfs never reach that critical fusion stage. The mystery lies in why some gas clouds form stars while others produce brown dwarfs instead. Is there a fundamental difference in the conditions that lead to their birth? Or are brown dwarfs simply failed stars that never accumulated enough mass? Some scientists believe that brown dwarfs form like stars, condensing from interstellar gas clouds but never gaining enough material to ignite fusion. Others argue that they might form like planets, growing within protoplanetary disks around larger stars before being ejected into space. If brown dwarfs can form in multiple ways, it could explain why they exist in such a wide range of sizes and temperatures. One of the biggest surprises in brown dwarf research is that many of them have weather. Unlike the relatively stable atmospheres of stars, brown dwarfs have turbulent clouds, high-speed winds, and even storms. Some of the first evidence of this came from observing brown dwarfs with infrared telescopes, which detected periodic changes in brightness, signs that thick clouds were swirling in and out of view. These clouds aren't made of water, like on Earth, but rather exotic materials such as molten iron, silicate dust, and ammonia. This discovery suggests that brown dwarfs have dynamic atmospheres, with complex weather patterns driven by heat and rotation. Some of them might even have giant storm systems that last for years, similar to Jupiter's Great Red Spot but on an even more extreme scale. The idea of a planet-sized object with clouds of liquid iron raining from the sky is something straight out of science fiction, yet it's a real possibility in the world of brown dwarfs. Another major question about brown dwarfs is whether they have moons or planetary systems. Since they don't shine as brightly as stars, detecting objects around them is much harder. But astronomers have found hints that some brown dwarfs may have planets orbiting them, just like normal stars do. These planets would be very different from Earth, most likely gas giants or icy worlds with thick atmospheres. If brown dwarfs can host planets, it raises the question of whether any of them could support life. A planet orbiting a brown dwarf would need to be extremely close to receive enough heat, but even then, the lack of steady fusion means that temperatures could fluctuate wildly. However, some scientists believe that life could exist in subsurface oceans, much like Jupiter's moon Europa or Saturn's moon Enceladus. These worlds might be warmed by geothermal activity rather than sunlight, creating a stable environment for life deep beneath the ice. Brown dwarfs also challenge our understanding of stellar populations. For decades, astronomers assumed that most of the mass in galaxies came from stars, but if brown dwarfs are more common than we thought, they could make up a significant portion of the missing mass in the universe. Some estimates suggest that for every visible star, there might be several brown dwarfs lurking undetected. This means that our current models of galaxy formation might need to be revised to account for this hidden population of objects. Another mystery is the possibility of brown dwarfs in our own solar system. While there's no direct evidence of a brown dwarf nearby, some astronomers have speculated about the existence of an unseen object influencing the orbits of distant Kuiper belt objects. This hypothetical object, sometimes called Planet 9, could be a brown dwarf, or a massive gas giant hiding in the far reaches of our solar system. If such an object exists, it could reshape our understanding of the solar system's structure. Brown dwarfs also play a role in binary star systems, where two objects orbit each other. In some cases, one member of a binary system is a brown dwarf, paired with a regular star. These systems help scientists understand the differences between brown dwarfs and low-mass stars, as well as how they interact gravitationally. Some brown dwarfs even orbit white dwarfs, dead stars that have exhausted their nuclear fuel, suggesting that they can survive in a wide range of environments. Perhaps the biggest question surrounding brown dwarfs is their ultimate fate. Since they don't undergo fusion, they don't explode as supernovae or collapse into black holes like massive stars do. Instead, they simply cool and fade over time. But this process takes trillions of years, far longer than the current age of the universe. This means that all the brown dwarfs that have ever formed are still out there, slowly radiating away their heat. In the distant future, as stars burn out and galaxies grow dark, brown dwarfs might be some of the last glowing objects left in the universe. Could they serve as cosmic embers, providing the final warmth in an otherwise frozen cosmos? If life ever emerges on a world orbiting a brown dwarf, could it be one of the last places where biology survives as the universe winds down? Ultimately, brown dwarfs represent one of the greatest frontiers in astronomy. They challenge our definitions of stars and planets, blur the line between different types of celestial objects, and hint at vast numbers of unseen bodies lurking in the darkness. As technology improves, we may one day uncover an entire hidden universe of brown dwarfs, revealing just how little we truly know about the cosmos. The search for brown dwarfs has become one of the most exciting fields in modern astronomy. Because they emit very little light, they are incredibly difficult to detect with traditional telescopes. Unlike stars, which shine brightly due to nuclear fusion, brown dwarfs only glow faintly in the infrared spectrum. This means that for decades, they were essentially invisible to astronomers, hiding in plain sight. It wasn't until the late 20th century, with the advent of powerful infrared telescopes, that we began to uncover their existence. One of the biggest breakthroughs in brown dwarf research came in 1995, when scientists using the 2-micron all-sky survey 2MASS discovered the first confirmed brown dwarf, Tide 1. Since then, thousands more have been identified, but astronomers believe that we've barely scratched the surface. The true population of brown dwarfs could be staggeringly high, potentially outnumbering stars in our galaxy. If that's the case, it would mean that a significant portion of the universe's mass is locked away in these dark, faint objects that are almost impossible to see with the naked eye. But how do we find something that barely emits light? The answer lies in infrared astronomy. Since brown dwarfs still radiate some heat, they glow in the infrared spectrum, even if they appear nearly invisible in visible light. Modern telescopes, like NASA's Spitzer Space Telescope and the James Webb Space Telescope, are specifically designed to detect this faint infrared glow. By scanning the sky in these wavelengths, astronomers have uncovered entire populations of brown dwarfs that were previously unknown. However, not all brown dwarfs are the same. They come in a range of temperatures and compositions, leading scientists to classify them into different types. The warmest brown dwarfs, known as L-type dwarfs, have temperatures of around 1,200 to 2,000 degrees Celsius and feature thick, cloudy atmospheres rich in metallic compounds. As they cool down, they transition into T-type dwarfs, which are cooler and have atmospheres dominated by methane, much like the gas giants in our solar system. The coldest brown dwarfs, known as Y-type dwarfs, have temperatures so low, sometimes just a few hundred degrees Celsius, that they could theoretically be mistaken for giant planets. Some Y dwarfs are barely warmer than a human body, making them among the coldest free-floating objects ever detected in space. One of the most mind-blowing discoveries about brown dwarfs is that they may be far more numerous than we ever imagined. In 2013, astronomers studying the WISE, Wide Field Infrared Survey Explorer, data found evidence suggesting that there might be nearly as many brown dwarfs as stars in the Milky Way. If this is true, then brown dwarfs could be a fundamental, yet hidden, component of our galaxy, shaping its structure in ways we don't yet understand. But the question remains, if brown dwarfs are so common, why didn't we notice them sooner? The answer lies in their extreme faintness. Unlike stars, which shine brightly across vast distances, brown dwarfs quickly lose their heat and fade into the darkness of space. They don't produce enough visible light to stand out in traditional sky surveys, meaning that for centuries, astronomers had no idea they even existed. Yet, despite their low visibility, brown dwarfs may hold the key to understanding some of the biggest mysteries in astrophysics. One of the most fascinating questions is whether brown dwarfs could explain part of the missing mass in the universe. While they don't account for dark matter, the invisible substance that makes up most of the universe's mass, they could still be a significant component of the so-called dark population of objects that are simply too faint for us to detect easily. Some researchers have even proposed that brown dwarfs could act as rogue planets, drifting through interstellar space without a host star. If true, this would mean that the galaxy is filled with countless wandering objects, each moving silently through the void, unseen and undetected. Some of these rogue brown dwarfs might have formed in isolation, while others could have been ejected from young planetary systems, cast out into the darkness by gravitational interactions with larger bodies. But perhaps the most exciting question about brown dwarfs is whether they could harbor life. At first glance, it might seem impossible. After all, brown dwarfs are cold, dim, and unstable compared to stars. However, some scientists believe that under the right conditions, certain planets orbiting brown dwarfs could maintain habitable environments. If a planet were close enough to a brown dwarf, it might receive just enough warmth to sustain liquid water, especially if it had a thick atmosphere or an internal heat source like tidal heating. Even more intriguing is the idea that life could exist deep within the clouds of a brown dwarf itself. Some researchers have speculated that the upper layers of a brown dwarf's atmosphere, where temperatures and pressures are more moderate, might support floating microbial life, similar to the hypothetical life forms proposed for Jupiter's atmosphere. While this idea is purely theoretical, it challenges our traditional assumptions about where life can exist in the universe. Brown dwarfs also raise fundamental questions about how planetary systems form. In traditional star systems, planets form from the leftover material in a protoplanetary disk, gradually growing through collisions and accretion. But what happens around a brown dwarf? If these objects can host their own planetary systems, it would suggest that planet formation isn't limited to stars. It can happen around failed stars as well. This has major implications for our understanding of exoplanets and the diversity of planetary systems throughout the galaxy. Even though we've learned a lot about brown dwarfs in the past few decades, there's still so much we don't know. How many are out there? Do they outnumber stars? Can they support life? Could there be brown dwarfs lurking in the farthest reaches of our own solar system? As telescopes become more advanced and our ability to detect faint objects improves, we may finally begin to answer these questions. But perhaps the greatest mystery of all is what brown dwarfs tell us about the future of the universe. Unlike stars, which burn out in spectacular explosions or collapse into black holes, brown dwarfs simply fade away. They cool down over trillions of years, becoming colder and darker until they are little more than faint, frozen husks drifting through space. In a distant future, long after the last stars have burned out, brown dwarfs might be some of the only remaining objects providing any light at all. In this way, brown dwarfs represent a glimpse into the far future, a universe where stars no longer shine, where the cosmos is dominated by faint, dying objects barely distinguishable from the surrounding darkness. They are a reminder that the universe is always changing, always evolving, and that even the smallest, dimmest objects can hold profound secrets about the nature of existence. Brown dwarfs exist in a strange middle ground between stars and planets, and their unique properties challenge our understanding of how celestial objects form and evolve. Unlike stars, brown dwarfs never reach the critical mass needed to sustain hydrogen fusion, but they are still much larger than even the biggest gas giant planets. This raises a fundamental question: where do we draw the line between a large planet and a small brown dwarf? Scientists use a rough mass threshold of around 13 times the mass of Jupiter as the dividing point. Anything below that is considered a planet, while anything above is a brown dwarf. However, this distinction isn't always clear-cut, and some objects blur the boundary between the two. One of the strangest aspects of brown dwarfs is their ability to generate heat despite not undergoing sustained fusion. In their early stages, brown dwarfs can fuse deuterium, a heavier isotope of hydrogen, but this process is short-lived. As they age, they cool down and gradually fade. However, some brown dwarfs exhibit surprisingly high levels of heat and activity, suggesting that other mechanisms might be at play. One possible explanation is internal gravitational contraction. Essentially, brown dwarfs slowly shrink over time, converting gravitational potential energy into heat. This process keeps them warm for billions of years, even in the absence of fusion. Another mystery surrounding brown dwarfs is their atmospheric composition. Unlike stars, which have relatively simple atmospheres dominated by hydrogen and helium, brown dwarfs have complex atmospheres filled with exotic chemicals. Some brown dwarfs have thick, swirling clouds of iron and silicate dust, while others contain high levels of ammonia, methane, and water vapor. The presence of these compounds suggests that brown dwarfs undergo dynamic weather patterns, similar to the stormy atmospheres of gas giant planets like Jupiter and Saturn. Some researchers even believe that brown dwarfs experience massive storms, with winds reaching thousands of kilometers per hour and lightning illuminating their dark, cloudy skies. The discovery of brown dwarf binary systems has added yet another layer of complexity to our understanding of these objects. Unlike regular stars, which often form in binary or multiple star systems, brown dwarfs were initially thought to be solitary objects. However, astronomers have since found numerous binary brown dwarfs, pairs of these failed stars orbiting each other. This raises an interesting question: how do brown dwarf pairs form, and why don't they collapse into a single, larger object? The prevailing theory is that some brown dwarfs form in dense star-forming regions but fail to accumulate enough mass to become full-fledged stars. Instead, they remain gravitationally bound to each other, drifting through space as a binary system. One of the strangest implications of brown dwarf research is the idea that some of these objects might be masquerading as rogue planets. A rogue planet is a planet that has been ejected from its original star system and now wanders the galaxy alone. While most rogue planets are thought to be smaller, gas giant-sized objects, some could be brown dwarfs that never formed around a star in the first place. These wandering brown dwarfs may be some of the loneliest objects in the universe, drifting through interstellar space without any light source to illuminate them. Despite their faint glow, brown dwarfs play an important role in the cosmic balance of our galaxy. Their sheer numbers suggest that they could have a significant gravitational influence, shaping the movement of stars and planetary systems. Some researchers have even speculated that brown dwarfs might be responsible for certain unexplained gravitational anomalies, possibly influencing the orbits of distant objects in our solar system. If a brown dwarf were lurking in the far outer reaches beyond the Kuiper Belt, it could explain some of the strange orbital patterns seen in trans-Neptunian objects. Another exciting aspect of brown dwarf research is their potential to host exoplanets. Although brown dwarfs are not true stars, they can still have their own planetary systems. Some brown dwarfs have been found with disks of dust and gas around them, similar to the protoplanetary disks that give rise to planets around regular stars. This suggests that under the right conditions, planets could form around brown dwarfs, creating miniature solar systems. However, because brown dwarfs emit very little light, any planets orbiting them would be in perpetual twilight, with only the faint infrared glow of their failed star to provide warmth. One of the biggest open questions in brown dwarf research is how many of these objects exist in the Milky Way. Current estimates suggest that for every regular star, there could be several brown dwarfs lurking in the darkness. If true, this would mean that brown dwarfs make up a significant fraction of the galaxy's total mass, yet they remain one of the least understood components of our cosmic neighborhood. Advanced infrared surveys, like those conducted by the James Webb Space Telescope, will likely reveal even more brown dwarfs, possibly uncovering entire populations that have remained hidden until now. But perhaps the most mind-boggling aspect of brown dwarfs is their potential role in the distant future of the universe. As the cosmos ages, regular stars will eventually burn out, leaving behind only remnants like white dwarfs, neutron stars, and black holes. However, brown dwarfs will persist, slowly cooling and fading but never truly disappearing. In a universe where stars have long since ceased to shine, brown dwarfs may be among the last remaining sources of heat and light, providing a final glimmer in an otherwise darkened cosmos. Brown dwarfs exist in a strange limbo between stars and planets, yet their presence raises profound questions about the nature of celestial formation. Unlike true stars, they never reach the critical mass needed to ignite hydrogen fusion, but their mass and composition set them apart from gas giants. This creates a unique class of objects that challenge the traditional definitions of planetary and stellar evolution. As scientists continue to study these enigmatic bodies, they uncover surprising details that reshape our understanding of how the universe constructs its celestial objects. One of the most puzzling aspects of brown dwarfs is their temperature and luminosity. Even though they lack sustained nuclear fusion, they still emit heat, particularly in the infrared spectrum. This glow comes primarily from gravitational contraction, a process where the brown dwarf's own mass slowly compresses under gravity, releasing energy in the form of heat. However, the rate of this heat release varies significantly among different brown dwarfs, suggesting that other processes could be at work. Some researchers hypothesize that certain brown dwarfs might generate internal heat through mechanisms not yet fully understood, possibly involving exotic states of matter under extreme pressure. Atmospheric composition is another area where brown dwarfs defy expectations. Observations reveal that their atmospheres are rich in elements typically associated with planetary weather systems, such as ammonia, methane, and water vapor. In fact, some brown dwarfs have cloud structures so dense that they resemble the stormy atmospheres of gas giants like Jupiter. Scientists have detected immense storm systems, with wind speeds potentially exceeding thousands of kilometers per hour, and some brown dwarfs may even experience atmospheric lightning. These discoveries suggest that, despite their classification as failed stars, brown dwarfs share surprising similarities with planets, further complicating the boundary between the two. Another fascinating revelation is the existence of brown dwarf pairs. Initially, astronomers assumed that most brown dwarfs formed in isolation, yet many have been discovered in binary systems, orbiting another brown dwarf, or even a low-mass star. These binary brown dwarfs challenge the traditional formation models, as their existence implies that brown dwarfs can form in a variety of ways, sometimes as failed stars, other times as oversized planets that never fully separated from their stellar nurseries. The presence of these binary systems raises new questions about their evolution. Do they form together in a collapsing cloud of gas, or do they capture each other through gravitational interactions? One of the most intriguing possibilities surrounding brown dwarfs is their potential as hosts for exoplanets. While conventional wisdom suggests that planets form around full-fledged stars, brown dwarfs possess circumstellar disks similar to those that give rise to planetary systems. Some brown dwarfs have been observed with protoplanetary disks, indicating that planet formation could occur in these environments. However, any planet orbiting a brown dwarf would experience extreme conditions. With little to no visible light from its host, such a planet would exist in perpetual twilight, illuminated only by the faint infrared glow of its parent body. This raises profound questions about the potential for habitability. Could life exist in such a dark and cold environment? The search for rogue planets has also led scientists to reevaluate the role of brown dwarfs in the galaxy. Some brown dwarfs may be masquerading as giant rogue planets, wandering through interstellar space without a host star. These objects blur the line between planet and star, making it difficult to classify them definitively. If brown dwarfs are as common as some models predict, they could significantly impact our understanding of galactic structure and evolution. Their gravitational influence, while subtle, could shape the motion of nearby celestial objects, possibly explaining some of the unexplained gravitational anomalies observed in deep space. In addition to their role as cosmic wanderers, brown dwarfs may hold the key to solving some of the universe's most perplexing mysteries. The fact that they do not undergo nuclear fusion means they cool over time, making them excellent natural laboratories for studying the physics of cooling stars and planetary atmospheres. By observing how their temperatures decrease over millions of years, astronomers can refine models that predict the thermal evolution of planets and stars alike. One of the most exciting frontiers in brown dwarf research is their potential contribution to dark matter studies. While brown dwarfs themselves do not constitute dark matter, their abundance and faint visibility raise the possibility that similar, yet undiscovered objects could be lurking in the universe, contributing to the missing mass problem. If large populations of faint brown dwarfs exist undetected, they could account for a portion of the unseen matter influencing galactic rotation and large-scale cosmic structures. Another unanswered question is the ultimate fate of brown dwarfs in the distant future of the universe. Unlike stars, which undergo dramatic transformations through supernovae or white dwarf formation, brown dwarfs simply cool and fade over time. Given enough time, trillions of years, brown dwarfs will become barely distinguishable from massive planets, radiating almost no detectable heat. In a universe where all stars have burned out, brown dwarfs could be among the last sources of warmth, glowing dimly in an otherwise frozen cosmos. The study of brown dwarfs is still in its early stages, and each new discovery brings more questions than answers. Their existence challenges the rigid categories of star and planet, forcing astronomers to rethink how celestial bodies form and evolve. As telescope technology improves and new observational techniques emerge, the coming decades will likely unveil even more astonishing details about these mysterious objects. The search for brown dwarfs continues, and with it, the possibility of uncovering deeper truths about the very nature of our universe. Brown dwarfs remain one of the most enigmatic objects in the universe, defying conventional classifications and challenging our understanding of celestial evolution. As astronomers continue to uncover more about these strange entities, new questions arise. How many truly exist? Are they more common than stars? Could they play a role in unexplored cosmic phenomena? The mystery deepens with every discovery, revealing that brown dwarfs are far from simple, failed stars, but rather complex, dynamic objects that may hold answers to some of the universe's biggest unknowns. One of the most baffling aspects of brown dwarfs is their sheer abundance. Some estimates suggest that for every visible star in the Milky Way, there may be several brown dwarfs lurking undetected in the darkness. If this is true, brown dwarfs could be one of the most numerous types of objects in the galaxy. The difficulty in detecting them arises from their low luminosity, as they emit most of their energy in the infrared spectrum rather than visible light. This means that for decades, countless brown dwarfs may have gone unnoticed, hidden among the vast stretches of interstellar space. Advanced infrared telescopes, such as the James Webb Space Telescope, have begun to reveal more of these elusive objects, but the question remains, how many are still undiscovered? The abundance of brown dwarfs raises another fascinating question about their influence on galactic structure. While individual brown dwarfs may have relatively weak gravitational effects compared to larger stars, their cumulative mass could shape the movement of entire star systems. Some researchers speculate that brown dwarfs might contribute to the gravitational anomalies observed in the outer regions of the Milky Way. If brown dwarfs are more common than previously thought, they could play a significant, yet largely unrecognized, role in shaping the orbits of nearby stars and planetary systems. Another mystery surrounding brown dwarfs is their role in planetary formation. Traditional models suggest that planets form within the circumstellar disks of young stars, but brown dwarfs have been found with their own planet-forming disks. This suggests that planets can emerge even in environments where full-fledged stars never formed. However, the conditions around brown dwarfs are vastly different from those around main-sequence stars, which raises new questions about the types of planets that might form in such environments. Could these planets support atmospheres? Could they have liquid water? And perhaps most intriguingly, could they harbor life? The question of life around brown dwarfs is particularly compelling. While brown dwarfs are not bright enough to provide the same level of warmth as a sun-like star, their residual heat could create habitable conditions on orbiting planets under the right circumstances. If a planet were to orbit close enough to a brown dwarf, it might receive enough infrared radiation to maintain liquid water on its surface. However, such a planet would likely experience extreme environmental conditions, including long periods of darkness and fluctuating temperatures. Despite these challenges, some scientists speculate that life could adapt to these conditions, potentially existing in subsurface oceans or relying on alternative forms of energy. Another area of interest in brown dwarf research is their weather patterns. Unlike most stars, brown dwarfs have complex atmospheres filled with turbulent storms, massive cloud formations, and even precipitation of exotic materials. Some brown dwarfs have been found with clouds composed of molten iron or silicate dust, creating dramatic and extreme weather systems. In some cases, these storms may be larger than entire planets, with wind speeds that dwarf anything seen on Earth. The presence of such weather patterns suggests that brown dwarfs are highly dynamic, constantly changing over time rather than remaining static and unchanging as once believed. One of the most significant discoveries in brown dwarf research is the presence of magnetic fields. While stars generate powerful magnetic fields through nuclear fusion processes, brown dwarfs do not undergo sustained fusion, making their magnetic activity more mysterious. Some brown dwarfs have been found to emit radio waves, a sign of strong magnetic activity similar to that seen in stars and even some planets. This raises the possibility that brown dwarfs have internal processes that generate magnetic fields in ways we do not yet fully understand. Could these magnetic fields influence their atmospheres, creating auroras similar to those seen on Earth and Jupiter? Could they interact with surrounding interstellar material in unexpected ways? Beyond their individual mysteries, brown dwarfs also hold significance in the broader story of cosmic evolution. Because they exist in a mass range between planets and stars, studying them provides insight into the processes that govern both stellar and planetary formation. Understanding how brown dwarfs form can help astronomers refine models of how stars develop in nebulae, how gas clouds collapse, and why some objects become stars while others do not. Brown dwarfs may also offer clues about the earliest stages of stellar evolution, potentially shedding light on how the first objects in the universe formed after the Big Bang. One of the most intriguing possibilities regarding brown dwarfs is whether they could serve as stepping stones to understanding even more exotic objects. If brown dwarfs represent one end of a spectrum that includes stars and planets, could there be other, Even stranger objects that exist just beyond our current classification systems? Are there hybrid celestial bodies that blur the line between brown dwarfs and fully formed stars? Could there be objects that failed to ignite nuclear fusion yet still exhibit properties unlike anything seen before? Another unsolved mystery is the fate of brown dwarfs in the distant future. Unlike stars, which eventually burn out, explode, or collapse into compact remnants, brown dwarfs have a different fate. Without nuclear fusion, they will continue cooling indefinitely, gradually fading over billions or even trillions of years. As the universe ages, brown dwarfs will become increasingly difficult to detect, eventually turning into dark, frozen remnants of their former selves. But could they still play a role in the far future of the cosmos? Some theories suggest that as stars burn out and the universe enters its so-called degenerate era, brown dwarfs may be among the last active objects left, faintly glowing as the final remnants of a once vibrant universe. Despite their relative obscurity, brown dwarfs are proving to be one of the most important pieces of the cosmic puzzle. They challenge long-held assumptions about what separates a planet from a star, reveal new possibilities for planetary formation, and hint at the existence of other yet undiscovered celestial phenomena. As observational technology improves and astronomers uncover more about these enigmatic objects, our understanding of the universe as a whole will likely shift in unexpected ways. Brown dwarfs may have started as an overlooked curiosity, dismissed as mere failed stars, but they are emerging as key players in the story of cosmic evolution. Their strange properties, unusual behavior, and sheer abundance suggest that they are far more than just an astronomical footnote. Instead, they represent a critical missing link between stars and planets, offering new avenues of discovery that could reshape our understanding of how the universe works. The mysteries surrounding them are vast, and the answers may lead to revelations far beyond what we currently imagine. Brown dwarfs are some of the strangest objects in the universe, occupying a bizarre space between planets and stars. They are too massive to be considered planets, but not massive enough to sustain the hydrogen fusion that powers true stars. This in-between state makes them one of the most intriguing and mysterious objects in astrophysics, raising endless questions about their formation, structure, atmosphere, evolution, and their potential role in shaping the galaxy. One of the biggest mysteries surrounding brown dwarfs is their formation. In the standard model of star formation, a dense cloud of gas and dust collapses under gravity, forming a protostar. If the mass of the collapsing cloud is high enough, nuclear fusion ignites, and a star is born. But brown dwarfs don't follow this path. They form like stars, yet never gain enough mass to trigger full hydrogen fusion. This raises the question, why do some collapsing clouds stop at brown dwarf size instead of growing into stars? Some theories suggest that turbulence, or radiation from nearby stars could prevent a forming brown dwarf from accumulating enough material to reach stellar status. Others propose that brown dwarfs may form in a fundamentally different way, perhaps through a process more similar to how giant planets develop in planetary systems. Another strange feature of brown dwarfs is their temperature. Despite not sustaining hydrogen fusion, brown dwarfs are not entirely cold. Young brown dwarfs can have surface temperatures exceeding thousands of degrees Fahrenheit, but over time, they gradually cool. This means that older brown dwarfs become progressively colder, some reaching temperatures only slightly higher than the outer planets of our solar system. This temperature range presents another puzzle. When does a brown dwarf stop being a failed star, and instead become a giant rogue planet? Some brown dwarfs may cool to the point where they resemble gas giants like Jupiter, making it difficult to distinguish between the two. The classification of brown dwarfs is another challenge. Astronomers have developed spectral types to categorize stars and brown dwarfs based on their temperatures and atmospheric compositions. Brown dwarfs fall into three main spectral classes, L, T, and Y. L dwarfs are the hottest and exhibit features similar to low-mass red dwarfs. T dwarfs are cooler, showing methane absorption in their atmospheres, similar to giant planets. Y dwarfs are the coldest known brown dwarfs, some with temperatures lower than the human body. These classifications help scientists understand the properties of brown dwarfs, but they also blur the line between brown dwarfs and planets. One of the most exciting discoveries in brown dwarf research is the existence of planetary mass brown dwarfs, objects that have masses similar to giant planets, but form like stars. These objects defy traditional definitions and challenge our understanding of what separates a planet from a star. If a brown dwarf is as small as Jupiter but forms through cloud collapse rather than planetary accretion, is it truly a failed star? Or is it a planet born through an unusual process? This question has led to debates in the scientific community about how to properly classify objects at the boundary between stars and planets. Another major area of interest is the atmospheres of brown dwarfs. Unlike stars, brown dwarfs have complex atmospheric layers filled with exotic elements and extreme weather patterns. Some brown dwarfs have been found with thick, stormy atmospheres, where massive cloud formations made of iron droplets or silicate dust swirl in turbulent currents. These storms can last for years, and their scale dwarfs even the most extreme storms on Jupiter. The presence of such complex weather patterns suggests that brown dwarfs are highly dynamic objects, changing in ways that are not yet fully understood. Some brown dwarfs also exhibit auroras, similar to those seen on Earth and Jupiter. These auroras are caused by interactions between the brown dwarf's magnetic field and charged particles in its atmosphere. But how do brown dwarfs generate such strong magnetic fields if they don't have the internal dynamo processes of stars? This remains an open question, but it suggests that brown dwarfs have hidden layers of complexity that challenge current models of astrophysics. The magnetic activity of brown dwarfs is particularly intriguing because it leads to radio emissions. Unlike ordinary stars, some brown dwarfs pulse with radio waves, signaling bursts of energy from their magnetic fields. This unexpected behavior raises questions about the internal structure of brown dwarfs, and whether they might have unknown processes generating these emissions. Could brown dwarfs have a type of magnetic dynamos similar to planets? Or is something else driving their radio bursts? One of the biggest challenges in studying brown dwarfs is detecting them in the first place. Since they emit little to no visible light, they remain hidden in the darkness, detectable only in the infrared spectrum. Infrared telescopes like the James Webb Space Telescope and the Wide Field Infrared Survey Explorer, WISE, have been instrumental in discovering new brown dwarfs, but many more remain undiscovered. Some astronomers believe that for every visible star in the galaxy, there could be multiple brown dwarfs lurking unseen. If this is true, brown dwarfs could be among the most common objects in the universe, yet they remain one of the least understood. This raises another fascinating possibility. Could brown dwarfs account for some of the missing mass in galaxies? While brown dwarfs alone are unlikely to explain dark matter, their abundance could contribute to the unseen mass that influences galactic rotation. If brown dwarfs are more numerous than we currently estimate, they could have a subtle but significant effect on the structure of the Milky Way and beyond. Brown dwarfs also challenge our understanding of planetary formation. Traditionally, planets are thought to form within the protoplanetary disks of stars. But brown dwarfs have been found with their own disks, suggesting that planet formation can occur even in environments without a fully formed star. Some brown dwarfs even have exoplanets orbiting them, further complicating the distinction between planets and stars. Could planets around brown dwarfs have the potential for habitability? While brown dwarfs emit little visible light, their infrared radiation could still provide warmth to planets with thick atmospheres. Some scientists speculate that life could exist on these worlds, adapting to the extreme conditions of a dimly lit environment. Another mystery is how brown dwarfs evolve over time. Unlike stars, which go through well-defined life cycles, brown dwarfs simply cool and fade. They don't explode in supernovae, collapse into neutron stars, or turn into white dwarfs. Instead, they remain as slowly cooling embers, gradually becoming colder and darker over billions of years. Some theories suggest that in the far future, brown dwarfs may cool so much that they become indistinguishable from giant rogue planets, drifting through the galaxy as dark, frozen remnants. Despite their lack of nuclear fusion, brown dwarfs may still play a role in galactic evolution. Because they form like stars but exist in an in-between state, studying brown dwarfs helps scientists refine models of how stars and planetary systems develop. Understanding why some objects become brown dwarfs while others become full-fledged stars could provide insights into the formation of entire galaxies. Another mystery surrounding brown dwarfs is their distribution. Some brown dwarfs exist alone, floating through interstellar space, while others are found in binary or even multiple star systems. But why do some brown dwarfs end up isolated while others remain in close orbits around other stars? One possibility is that many brown dwarfs originally formed as companions to larger stars but were later ejected due to gravitational interactions. If this is the case, there could be countless rogue brown dwarfs wandering the galaxy, remnants of disrupted star systems. The search for brown dwarfs has also led to surprising discoveries about their brightness. Some brown dwarfs emit unexpected bursts of light, despite not having sustained nuclear fusion. These flares may be caused by atmospheric processes, magnetic interactions, or other unknown mechanisms. The fact that brown dwarfs can exhibit such variability suggests that they are not just passive, cooling objects but instead undergo dynamic changes over time. Even after decades of research, brown dwarfs continue to surprise astronomers with their unexpected properties. Every new discovery adds another layer of complexity to our understanding of these strange objects. As technology advances and telescopes become more powerful, more brown dwarfs will undoubtedly be discovered, shedding further light on their role in the cosmos. But for now, they remain one of the greatest unsolved mysteries in astrophysics, silent wanderers in the vast darkness of space, waiting to reveal their secrets. Brown dwarfs remain one of the biggest astrophysical mysteries, blurring the boundaries between planets and stars. Their existence challenges long-held theories of stellar and planetary formation, and their peculiar characteristics defy easy classification. As astronomers continue to discover more brown dwarfs, new questions emerge, deepening the mystery of these celestial objects. One of the most puzzling aspects of brown dwarfs is their internal structure. Unlike true stars, which have a well-defined core where nuclear fusion occurs, brown dwarfs lack the necessary mass to sustain hydrogen fusion. However, this does not mean they are entirely inert. In fact, brown dwarfs still undergo some limited fusion processes early in their lifetimes. The most notable of these is the fusion of deuterium, a heavier isotope of hydrogen. Deuterium fusion occurs at much lower temperatures than the fusion of regular hydrogen, allowing brown dwarfs to briefly generate some energy in their early stages. This fusion process provides a temporary source of heat, slowing the cooling of young brown dwarfs. However, deuterium is relatively scarce in the universe, and once a brown dwarf depletes its supply, it enters a slow cooling phase that lasts for billions of years. The rate at which a brown dwarf cools depends on its mass, composition, and surrounding environment, making it difficult to predict its long-term evolution with certainty. Another mystery concerns the outer layers of brown dwarfs. Unlike stars, which have well-defined atmospheres dictated by powerful radiation and convection processes, brown dwarfs have much more complex and unpredictable atmospheric dynamics. Observations suggest that many brown dwarfs experience massive storm systems, some of which can be thousands of kilometers wide. These storms resemble those seen on gas giants like Jupiter, but on a much larger and more chaotic scale. The composition of these storms is another intriguing puzzle. Infrared spectroscopy has revealed that brown dwarf atmospheres contain elements such as iron, silicates, and even exotic compounds that do not naturally occur in the atmospheres of stars. Some brown dwarfs have clouds made of tiny rock particles or even droplets of molten metal. The presence of such extreme atmospheric conditions suggests that brown dwarfs exist in a highly dynamic state, with constant turbulence reshaping their outer layers over time. One particularly fascinating discovery is that some brown dwarfs exhibit periodic brightness fluctuations. This suggests that they may have rotating cloud patterns or surface features that cause changes in their emitted light. These variations can provide important clues about the internal structure and weather patterns of brown dwarfs. However, interpreting these fluctuations is difficult, as brown dwarfs lack the strong convective processes that drive weather patterns on planets like Earth. The question of whether brown dwarfs have solid cores is another topic of debate among scientists. Gas giants like Jupiter are believed to have rocky or metallic cores buried deep beneath their thick atmospheres. If brown dwarfs form through a similar mechanism, they might also have solid cores. However, if brown dwarfs truly form like stars, they may be entirely gaseous with no defined core at all. Determining the internal composition of a brown dwarf is nearly impossible with current technology, making this one of the most elusive questions in astrophysics. Another mystery is the relationship between brown dwarfs and planetary systems. Some brown dwarfs have been found with disks of gas and dust surrounding them, much like the protoplanetary disks around young stars. These disks suggest that brown dwarfs could host planets, just like stars do. If planets can form around brown dwarfs, this raises the possibility of entirely new types of planetary systems that do not rely on a central star for heat and light. Planets orbiting brown dwarfs would exist in an environment unlike anything found in our solar system. Instead of being bathed in the light of a bright star, these planets would receive only faint infrared radiation, making their climates much colder and more extreme. However, if these planets have thick atmospheres capable of trapping heat, or if they experience tidal heating from interactions with their host brown dwarf, they could still support liquid water and possibly even life. This leads to one of the most intriguing questions in astrobiology. Could life exist on planets orbiting brown dwarfs? While brown dwarfs are not as luminous as stars, they still emit infrared radiation that could provide a stable energy source for certain forms of life. Some scientists speculate that microbial life could adapt to the low-light conditions of a brown dwarf system, evolving to use infrared radiation instead of visible light. If such life exists, it would challenge our understanding of habitability and expand the potential environments where life might be found in the universe. Another possibility is that brown dwarfs themselves could host exotic life forms. While traditional life as we know it depends on stable energy sources and chemical reactions, some theorists have proposed the idea of plasma-based life forms that could exist within the dense atmospheres of brown dwarfs. Such life would be radically different from anything on Earth, relying on electromagnetic interactions rather than organic chemistry. While this remains purely speculative, it raises fascinating questions about the potential for life in extreme environments. One of the most surprising discoveries in recent years is that some brown dwarfs have strong magnetic fields, comparable to those of fully fledged stars. These magnetic fields can produce powerful auroras, similar to those seen on planets like Jupiter and Saturn. However, the exact mechanism behind these auroras remains a mystery. Unlike planets, which generate auroras through interactions with a host star's radiation, brown dwarfs produce auroras on their own. This suggests that brown dwarfs may have hidden internal processes generating these magnetic fields, possibly through mechanisms similar to those seen in planets. Another major challenge in studying brown dwarfs is their detection. Because they emit very little visible light, they are nearly impossible to observe with traditional optical telescopes. Instead, astronomers rely on infrared surveys to locate them. Some of the most important discoveries have come from missions like WISE and the James Webb Space Telescope, which are capable of detecting the faint infrared glow of distant brown dwarfs. However, many brown dwarfs remain hidden, and astronomers believe that the Milky Way may contain billions of undiscovered brown dwarfs. If brown dwarfs are as common as some models predict, they could have significant implications for our understanding of galactic evolution. While brown dwarfs themselves do not contribute much to stellar populations, their presence could influence the dynamics of star formation and planetary system development. Some researchers have suggested that brown dwarfs may even act as failed companions in binary systems, altering the evolution of their neighboring stars. Another open question is whether brown dwarfs could serve as stepping stones between planetary and stellar evolution. If a brown dwarf gains additional mass through accretion or mergers, could it eventually ignite hydrogen fusion and become a full-fledged star? While this scenario is unlikely under normal circumstances, it remains a possibility in dense star-forming regions where interactions between objects are common. Some theories also suggest that brown dwarfs could be linked to rogue planets. Rogue planets are planetary-sized objects that drift freely through space without orbiting a star. It is possible that some of these rogue planets were once brown dwarfs that cooled to the point where they became indistinguishable from giant planets. If this is the case, the boundary between brown dwarfs and planets may be even more blurred than previously thought. As our understanding of brown dwarfs continues to evolve, new discoveries will likely challenge our existing models of astrophysics. Whether they are failed stars, oversized planets, or something entirely different, brown dwarfs remain one of the greatest enigmas in the universe. Each new observation provides a glimpse into the strange physics governing these objects, but many questions remain unanswered. The study of brown dwarfs is still in its early stages, and future telescopes will undoubtedly reveal more about their nature. Upcoming missions, such as next-generation infrared observatories, will allow scientists to detect even colder and more distant brown dwarfs, expanding our knowledge of these elusive objects. With each discovery, the mystery of brown dwarfs deepens, reminding us that the universe is far more complex and mysterious than we ever imagined. Brown dwarfs challenge the way we think about celestial classification, and their existence raises deep questions about the nature of stellar and planetary formation. These objects blur the lines between what we traditionally define as stars and planets, yet they follow unique evolutionary paths that set them apart from both. As astronomers uncover more about their properties, the mysteries surrounding them only grow. One of the most intriguing aspects of brown dwarfs is their formation process. Unlike stars, which form from collapsing clouds of gas and dust that reach sufficient mass to ignite hydrogen fusion, brown dwarfs are thought to form in a similar manner but fail to accumulate enough mass to sustain this process. However, some theories suggest that brown dwarfs might also form like giant planets, accumulating mass from a protoplanetary disk around a larger star. This dual possibility adds complexity to our understanding of their origins, and determining which formation process is more common remains an ongoing challenge in astrophysics. Another significant mystery is their mass distribution. Brown dwarfs are defined as objects with masses between roughly 13 and 80 times that of Jupiter. However, there is no clear dividing line between the smallest brown dwarfs and the largest gas giant planets. Some exoplanets discovered in recent years have masses comparable to brown dwarfs, yet they orbit stars like regular planets. This raises the question, where does a massive planet end and a low-mass brown dwarf begin? Some researchers argue that formation history, rather than mass, should be the defining factor. If an object forms in a disk around a star, it is considered a planet. If it forms independently, it is a brown dwarf. But this distinction is not always easy to determine, especially for objects that exist in isolation. One of the most surprising discoveries about brown dwarfs is that they can exist in binary systems. While it was once assumed that brown dwarfs were mostly solitary objects, astronomers have found many cases where brown dwarfs orbit one another or even orbit a larger star. In some cases, brown dwarfs are found in binary pairs where both objects have similar masses, leading to systems where neither object is a true star. These binary brown dwarf systems challenge traditional models of stellar formation, as it was previously thought that low-mass objects like brown dwarfs would have difficulty forming in pairs due to the way gas clouds fragment during collapse. The discovery of brown dwarf binaries suggests that their formation is more complex than previously believed. Another major mystery concerns the temperatures of brown dwarfs. When they are young, brown dwarfs are relatively warm due to the residual heat from their formation. Over time, however, they gradually cool as they lose energy. The coolest brown dwarfs, known as white dwarfs, have temperatures as low as room temperature on Earth. This is remarkable because it means some brown dwarfs could theoretically have environments cold enough for complex chemistry to occur, raising questions about their potential to host exotic forms of life. The discovery of extremely cold brown dwarfs has also blurred the line between these objects and rogue planets, which are planets that drift freely through space without a host star. Some of the coldest brown dwarfs resemble gas giants like Jupiter more than they do small stars, reinforcing the idea that the boundary between planets and brown dwarfs is not well defined. The atmospheres of brown dwarfs are another fascinating area of study. Unlike stars, which have relatively simple compositions dominated by hydrogen and helium, brown dwarfs can have highly varied atmospheres rich in complex molecules. Observations have detected water vapor, methane, and even ammonia in brown dwarf atmospheres. Some brown dwarfs also exhibit signs of silicate and metal clouds, meaning that these objects could have weather systems far more extreme than anything seen on Earth. In some cases, brown dwarfs have shown evidence of massive storms, with wind speeds that dwarf anything found in the solar system. The nature of these storms and their impact on brown dwarf evolution remain active areas of research. One of the most unusual discoveries in recent years is that some brown dwarfs exhibit radio emissions, a phenomenon typically associated with planets that have strong magnetic fields. These emissions suggest that brown dwarfs generate magnetic activity similar to planets like Jupiter. However, the source of these emissions is still not fully understood, as brown dwarfs lack the internal dynamo mechanisms found in stars. Some researchers speculate that these radio emissions could be caused by interactions with unseen planetary companions or by previously unknown magnetic processes occurring within brown dwarfs themselves. The presence of magnetic fields in brown dwarfs raises additional questions about their internal structure. While stars generate magnetic fields through convective processes in their interiors, brown dwarfs do not have the same level of internal convection. This means that their magnetic fields must be generated by alternative mechanisms. Understanding how these fields form and evolve could provide new insights into the physics of substellar objects, and help explain why some brown dwarfs exhibit strong magnetic activity while others do not. Another unresolved question is how common brown dwarfs are in the galaxy. Early estimates suggested that brown dwarfs might be as numerous as stars, but more recent studies indicate that they are less common than initially thought. However, this could be due to observational limitations, as brown dwarfs are faint and difficult to detect. Infrared surveys have revealed that brown dwarfs are found in a wide range of environments, from dense star-forming regions to the isolated depths of interstellar space. Some astronomers believe that many more brown dwarfs remain undiscovered, hidden in the vastness of the galaxy. One particularly intriguing area of study is the potential for brown dwarfs to host planetary systems. While brown dwarfs do not have the same level of gravitational influence as stars, they are still capable of capturing and holding on to planetary companions. Observations have confirmed that some brown dwarfs have disks of dust and gas, similar to the protoplanetary disks found around young stars. These disks suggest that planets could form around brown dwarfs in much the same way they do around stars. If this is the case, it raises the possibility of an entirely new category of planetary systems, where planets orbit brown dwarfs instead of traditional stars. The question of habitability in brown dwarf systems is another topic of intense debate. While brown dwarfs do not emit enough light to support traditional habitable zones like those found around stars, they still emit infrared radiation, which could provide a heat source for planets with thick atmospheres. Some researchers speculate that if a planet orbiting a brown dwarf has a dense enough atmosphere to trap heat, it could maintain liquid water on its surface. Additionally, if the planet experiences tidal heating due to gravitational interactions with its host brown dwarf, this could provide another potential energy source for sustaining habitability. Some theories even suggest that life could exist within the atmospheres of brown dwarfs themselves. While this idea is highly speculative, it is based on the notion that complex chemical reactions could take place in the upper layers of brown dwarf atmospheres, where temperatures and pressures are more moderate. If this is the case, brown dwarfs could represent an entirely new class of environments capable of supporting exotic forms of life. As new telescopes and observational techniques become available, our understanding of brown dwarfs will continue to grow. The James Webb Space Telescope and other next-generation observatories are expected to provide unprecedented insights into the composition, structure, and evolution of brown dwarfs. These discoveries could help answer some of the biggest questions about these enigmatic objects while also raising new ones. Ultimately, brown dwarfs remain one of the most fascinating mysteries in astrophysics. They challenge traditional definitions of stars and planets, exhibit unique physical properties, and may even hold clues about the potential for life in the universe. With each new discovery, our understanding of these strange objects deepens, but many fundamental questions remain unanswered. As scientists continue to explore the mysteries of brown dwarfs, they may uncover new insights that reshape our understanding of the cosmos itself. brown dwarfs sit in an enigmatic realm between stars and planets, and their study has revealed some of the most unexpected mysteries of astrophysics. While we now know that they exist in great numbers, their true nature remains elusive. They are too small to sustain hydrogen fusion like stars, yet they are too massive to be considered traditional planets. But what makes them even more intriguing is the variety of their characteristics. Some are hot and glowing, while others are cold and barely distinguishable from rogue planets. Their atmospheres are chaotic, their magnetic fields are puzzling, and their origins are still up for debate. Every discovery about brown dwarfs seems to raise more questions than answers. One of the biggest mysteries surrounding brown dwarfs is their initial formation. While they are believed to form in a way similar to stars, the exact process is still uncertain. Some theories suggest that brown dwarfs are simply failed stars, objects that began forming like regular stars but didn't accumulate enough mass to sustain fusion. Others propose that brown dwarfs form through a separate process, one that is more similar to planet formation. If this is the case, then brown dwarfs may not be a singular category of objects, but rather a mix of different formations that only appear similar on the surface. Another mystery is why brown dwarfs appear to be less common than originally expected. Some early models predicted that brown dwarfs should be as common as stars, if not more so, yet surveys of the night sky have found fewer than anticipated. This could be due to limitations in our ability to detect them, as brown dwarfs are faint and radiate most of their energy in infrared wavelengths. However, it is also possible that their formation is inherently less efficient than that of stars, meaning that fewer of them come into existence. The question of their abundance is still unresolved, and ongoing infrared sky surveys may eventually shed light on just how many brown dwarfs are out there. The temperature evolution of brown dwarfs is another intriguing aspect of their existence. Unlike stars, which maintain a relatively stable temperature due to nuclear fusion, brown dwarfs cool over time. When they are young, they can be hot enough to glow with a reddish hue, but as they age, they gradually fade into cooler, darker objects. The coolest known brown dwarfs, classified as white dwarfs, have temperatures comparable to a warm summer day on Earth. This cooling process means that older brown dwarfs become nearly invisible, making them incredibly difficult to detect. It is possible that many ancient brown dwarfs exist throughout our galaxy, but we simply cannot see them. One of the most perplexing discoveries about brown dwarfs is their weather patterns. Observations have shown that brown dwarfs have dynamic atmospheres with massive storms, cloud formations, and even shifting weather systems. Unlike planets in our solar system, which have relatively stable climates, brown dwarfs can exhibit rapid and extreme atmospheric changes. Some brown dwarfs have been observed to brighten and dim over short periods, suggesting that enormous storm systems may be forming and dissipating in their atmospheres. These weather patterns are unlike anything seen on Earth or in the gas giants of our solar system, raising questions about what drives these extreme atmospheric changes. The atmospheres of brown dwarfs also contain unexpected chemical signatures. Unlike stars, which are mostly hydrogen and helium, brown dwarfs can have complex molecules like water vapor, methane, ammonia, and even possible signs of organic chemistry. This has led some researchers to speculate that brown dwarfs could host unique chemical processes that might be relevant to the origins of life. Some brown dwarfs have even shown evidence of cloud layers made of minerals like silicates, suggesting that their skies could be filled with molten rock particles suspended in the air. These exotic atmospheric conditions make brown dwarfs some of the most unusual objects in the universe. Another major puzzle is their magnetic fields. Brown dwarfs, despite lacking the internal fusion processes that power stellar magnetic fields, have been observed emitting strong radio waves. These emissions indicate that brown dwarfs generate magnetic activity similar to planets like Jupiter. However, the mechanism behind this remains unknown. Some brown dwarfs exhibit aurora-like emissions, similar to the northern lights seen on Earth, but on a vastly larger scale. The presence of strong magnetic fields in brown dwarfs challenges existing models of how these objects function, as they do not have the same convective interiors as stars. Brown dwarfs also defy expectations when it comes to their companions. While they were initially thought to be mostly solitary, astronomers have discovered that many brown dwarfs exist in binary systems, either orbiting another brown dwarf, or even orbiting a full-fledged star. Some brown dwarfs are found with planetary companions, raising questions about whether those planets formed around the brown dwarf or were captured from elsewhere. The presence of planetary systems around brown dwarfs suggests that planet formation can occur under a wide range of conditions, not just around traditional stars. One of the most controversial ideas surrounding brown dwarfs is whether they could host habitable worlds. While brown dwarfs do not emit enough light to support an Earth-like habitable zone, some researchers speculate that planets orbiting close to a brown dwarf could still retain liquid water under the right conditions. If a planet has a thick enough atmosphere to trap heat, it could potentially remain warm even in the dim light of a brown dwarf. Additionally, tidal heating, where the gravitational pull of the brown dwarf causes internal friction within the planet, could provide an additional source of heat. This raises the possibility that life could exist on planets orbiting brown dwarfs, even in the absence of strong sunlight. Another speculative idea is that life could potentially exist within the atmospheres of brown dwarfs themselves. While this might sound far-fetched, some researchers have suggested that the upper layers of brown dwarf atmospheres, where temperatures and pressures are more moderate, could provide conditions for exotic forms of life. This would be a completely different kind of biology from anything we know, but if complex chemistry can occur in these atmospheres, then brown dwarfs might be home to microbial-like organisms floating in the clouds. Future discoveries will likely reshape our understanding of brown dwarfs. With next-generation telescopes like the James Webb Space Telescope, astronomers are now able to study brown dwarfs in greater detail than ever before. These observations could reveal new insights into their atmospheric composition, magnetic activity, and potential for hosting planets. Additionally, as infrared sky surveys continue, more brown dwarfs are expected to be discovered, helping to answer the question of how common they really are in the galaxy. In many ways, brown dwarfs are a reminder of how little we still know about the universe. They exist in the gray area between stars and planets, defying easy categorization and challenging traditional models of astrophysics. Every new discovery about brown dwarfs seems to lead to even deeper mysteries, from their strange weather patterns to their unexpected magnetic activity. As our observational technology improves, we may finally be able to answer some of the biggest questions about these elusive objects. But for now, brown dwarfs remain one of the most fascinating and perplexing mysteries in the cosmos. Brown dwarfs represent an extraordinary class of celestial objects that exist in a liminal state between planets and stars. Their study has continued to uncover some of the most perplexing mysteries in astrophysics, challenging our understanding of stellar formation, planetary evolution, and the fundamental physics governing these strange objects. While we have made significant progress in identifying and characterizing brown dwarfs, the more we learn, the more questions arise. Their elusive nature, faint luminosity, and peculiar properties make them some of the most difficult objects to study in the universe. Yet, despite these challenges, brown dwarfs continue to captivate astronomers, fueling new theories and discoveries. One of the biggest open questions is the exact mechanism behind their formation. Traditional star formation models suggest that brown dwarfs should form in much the same way as stars, through the gravitational collapse of gas and dust in a molecular cloud. However, the fact that brown dwarfs fail to accumulate enough mass to sustain hydrogen fusion raises doubts about whether this process alone can account for their existence. Some researchers propose that brown dwarfs might form in a way similar to planets, growing from the accumulation of material within a protoplanetary disk. If this is true, then brown dwarfs could represent an entirely separate class of objects with a different formation pathway than stars. Another major mystery is why brown dwarfs do not appear to be as abundant as originally predicted. Early simulations suggested that brown dwarfs should be as common, if not more so, than main-sequence stars. However, observational surveys have found fewer brown dwarfs than expected. This discrepancy could be due to detection limitations, as brown dwarfs emit most of their radiation in the infrared spectrum and become increasingly difficult to observe as they cool. Alternatively, it may suggest that brown dwarf formation is inherently less efficient than stellar formation. This leads to another critical question. If brown dwarfs form like stars, what prevents them from becoming fully fledged stars? If they form like planets, why are they so much larger than known planetary objects? Adding to the enigma is the fact that some brown dwarfs exhibit characteristics that overlap with both planets and stars. Their atmospheres, for instance, are incredibly diverse, featuring dynamic cloud formations, storms, and even elements associated with rocky planets. Some brown dwarfs have been observed with weather systems that are highly variable, suggesting a level of atmospheric turbulence that rivals even the most extreme planetary environments. The presence of clouds made of exotic materials, including molten iron and silicates, paints a picture of worlds that are entirely alien to anything found in our solar system. The complexity of these atmospheres has led some scientists to speculate that brown dwarfs might serve as analogues for exoplanets, allowing us to study planetary atmospheres in a way that would be impossible with direct exoplanet observations. Perhaps one of the most perplexing findings related to brown dwarfs is their unexpected magnetic activity. Despite their lack of hydrogen fusion and the internal dynamo processes that generate magnetic fields in stars, brown dwarfs have been detected emitting strong radio waves. Some exhibit aurora-like emissions similar to Jupiter's, raising the question of how these magnetic fields are being generated. The presence of magnetic fields suggests that brown dwarfs may have internal processes that are not yet fully understood. Given that they lack the convective energy of a main sequence star, this remains one of the greatest mysteries in brown dwarf research. Beyond their magnetic properties, the rotational speeds of brown dwarfs are another puzzling factor. Many brown dwarfs rotate at astonishing speeds, some completing a full rotation in just a few hours. This is significantly faster than most stars and planets, raising questions about how they attain such high rotational velocities. One hypothesis is that they experience very little braking from stellar winds, allowing them to maintain their initial spin rate throughout their lifetimes. However, some brown dwarfs have been found to rotate much slower than expected, suggesting that there may be unknown mechanisms at play that influence their angular momentum over time. Another unsolved mystery is the existence of binary brown dwarf systems. While stars commonly form in binary or even multistar systems, brown dwarfs were initially thought to be predominantly solitary objects. However, observations have revealed that many brown dwarfs exist in binary pairs, sometimes even orbiting one another in configurations that defy conventional models of star system formation. Some brown dwarfs have even been found orbiting main sequence stars, leading to speculation about whether they formed alongside their host star or were later captured. These binary systems provide valuable insights into the formation and evolution of brown dwarfs, yet they also complicate our understanding of how these objects originate. The discovery of planetary systems around brown dwarfs adds yet another layer of complexity to their story. Some brown dwarfs have been found with planet-like companions, suggesting that planetary formation is not limited to traditional stars. However, the exact mechanism behind these planetary systems remains unclear. Did these planets form in a protoplanetary disk around the brown dwarf, similar to how planets form around stars? Or were they captured from another system? The presence of planetary companions challenges existing models of planet formation and suggests that planetary systems may be more diverse than previously imagined. One of the most intriguing questions about brown dwarfs is whether they could host habitable environments. While brown dwarfs themselves do not generate enough energy to support an Earth-like habitable zone, it is possible that their planetary companions could retain heat through thick atmospheres or tidal heating. Some researchers speculate that exomoons orbiting planets around brown dwarfs could be potential candidates for habitability, provided they have the right atmospheric conditions. Additionally, the upper atmospheres of some brown dwarfs may have temperatures and pressures suitable for complex chemistry, raising the speculative possibility of life in the clouds of these enigmatic objects. As observational technology improves, our understanding of brown dwarfs will continue to evolve. The James Webb Space Telescope and future infrared observatories will allow astronomers to peer deeper into the atmospheres of brown dwarfs, potentially unlocking new insights into their composition and behavior. Additionally, continued sky surveys will likely uncover more brown dwarfs, helping to refine estimates of their abundance and distribution in the galaxy. With each new discovery, Brown dwarfs are proving to be far more complex and diverse than originally thought, reinforcing the idea that they are not merely failed stars but rather unique astronomical entities that challenge our fundamental understanding of celestial objects. In many ways, brown dwarfs serve as a bridge between the known and the unknown. They blur the lines between stars and planets, forcing us to rethink our classifications and expand our definitions of what constitutes a celestial body. Every discovery about brown dwarfs seems to lead to new questions, making them one of the most compelling and mysterious objects in the universe. As our ability to observe these objects improves, we may one day unravel the secrets of their formation, evolution, and potential role in the broader cosmic landscape. But for now, brown dwarfs remain one of the great unsolved mysteries of modern astronomy. Brown dwarfs challenge everything we thought we understood about celestial objects, existing in a strange in-between state that defies simple categorization. They are too massive to be considered planets, yet too small to ignite the sustained nuclear fusion that defines stars. As a result, they sit in a peculiar limbo, glowing faintly with the remnants of their initial formation heat, while slowly cooling over billions of years. But the more we study these strange objects, the more anomalies we discover, raising new questions about their origins, their properties, and their role in the grand structure of the universe. One of the biggest unresolved mysteries surrounding brown dwarfs is how their atmospheres evolve over time. Unlike stars, which have relatively well-understood spectral classifications, brown dwarfs exhibit atmospheric compositions that change dramatically as they cool. When they are young and still radiating residual heat from their formation, their atmospheres resemble those of very cool stars, dominated by hydrogen and helium. However, as they cool further, they start to develop complex cloud formations composed of iron, silicates, and even more exotic elements. These clouds cause dramatic shifts in their observed brightness, leading to unpredictable variations in their light curves. Some brown dwarfs have been observed undergoing extreme brightness fluctuations within just a few hours, suggesting that their atmospheres experience massive storms and chaotic weather patterns. This variability is similar to what we see on gas giant planets like Jupiter, but on a much larger scale. Some researchers believe that these weather systems could be caused by rapid rotation combined with convection-driven storms, resulting in enormous cloud formations that periodically block and reveal different layers of the brown dwarf's atmosphere. If this is true, then studying brown dwarfs could give us unprecedented insights into the behavior of exoplanet atmospheres, especially those of hot Jupiters and other gas giants that orbit close to their parent stars. Another major question is how brown dwarfs fit into the broader spectrum of stellar and planetary evolution. If brown dwarfs form like stars, then we would expect to see a continuous distribution of objects from low-mass stars down to the smallest brown dwarfs. However, some observational studies suggest that there may be a gap in the mass distribution, indicating that brown dwarfs do not form as frequently as expected. This has led some astronomers to propose that brown dwarfs might require unique conditions to form, or that many of them may simply be ejected from their birth environments before they can be detected. One particularly intriguing idea is that brown dwarfs might be failed binary stars. In this scenario, a pair of stars forms in a binary system, but one of them fails to accumulate enough mass to sustain nuclear fusion. Instead of becoming a fully fledged star, it remains a brown dwarf, doomed to slowly cool over billions of years. Some brown dwarfs have been found in wide orbits around stars, lending some support to this idea. However, many brown dwarfs appear to be isolated, raising the question of whether they formed alone or were ejected from their original systems. The existence of free-floating brown dwarfs, sometimes called rogue planets, is another perplexing mystery. Some brown dwarfs have been found drifting through interstellar space with no obvious companion star. These objects challenge our understanding of planetary formation because they suggest that planets might be able to form independently, outside of traditional star systems. If brown dwarfs can exist as isolated objects, it raises the possibility that there could be billions of rogue planets wandering the galaxy, many of them undetectable due to their faint infrared emissions. One of the most exciting areas of research involving brown dwarfs is the search for exoplanets orbiting these objects. If brown dwarfs can host planetary systems, then studying them could provide valuable insights into the diversity of planetary formation processes. Some brown dwarfs have already been found with planetary mass companions, but the exact nature of these relationships remains unclear. Are these true planetary systems, or are the companions simply smaller brown dwarfs that formed through a separate mechanism? The answer to this question could have profound implications for our understanding of how planets and stars are related. Another unresolved issue is the internal structure of brown dwarfs. Unlike stars, which have well-defined cores and radiative zones, brown dwarfs are thought to be fully convective, meaning that their interiors are constantly mixing. This has significant implications for their evolution because it means that heat and material are distributed throughout the entire object rather than being concentrated in a central core. However, the details of this convective mixing are not well understood, and different models predict different outcomes for how brown dwarfs cool and change over time. Adding to the mystery is the fact that some brown dwarfs exhibit unusual chemical compositions that do not match what we would expect based on their formation models. Some have been found with unexpectedly high levels of certain elements, suggesting that they may have formed in environments different from those of normal stars. Others appear to have anomalous surface features that defy current explanations. These oddities suggest that brown dwarfs may have a much more complex evolutionary history than we currently realize. Another area of active research is the search for brown dwarfs in star-forming regions. If brown dwarfs form in the same way as stars, then they should be present in large numbers in regions where new stars are being born. However, surveys of these regions have sometimes yielded fewer brown dwarfs than expected. This suggests that either brown dwarfs form through a different process, or that many of them are simply too faint to detect with current telescopes. Future observations with advanced infrared telescopes may help resolve this issue by allowing us to peer deeper into star-forming clouds and identify more brown dwarfs. Brown dwarfs also raise questions about the lower mass limit of what can be considered a star. The boundary between the smallest stars and the largest brown dwarfs is not entirely clear, and some objects appear to straddle this divide. Theoretically, an object must have at least about 75 times the mass of Jupiter to sustain hydrogen fusion and become a true star. However, some brown dwarfs exhibit properties that suggest they might have briefly ignited fusion in the past before cooling down. This raises the possibility that some brown dwarfs might be failed stars that came extremely close to achieving stellar status but fell just short. Despite all these open questions, brown dwarfs continue to provide astronomers with valuable insights into the fundamental processes that govern celestial objects. Their study has already led to breakthroughs in our understanding of atmospheric physics, magnetic fields, and planetary formation. As new telescopes and observational techniques come online, we will likely discover even more surprises about these enigmatic objects. In many ways, brown dwarfs are a cosmic puzzle that challenges our assumptions about how stars and planets form and evolve. They exist on the fringes of our classification systems, blurring the line between what we consider a star and what we consider a planet. Yet, it is precisely this ambiguity that makes them so fascinating. They force us to rethink our models, to refine our theories, and to explore new possibilities in the vast, uncharted expanse of the universe. With each new discovery, brown dwarfs remind us that the universe is far more complex than we ever imagined. They are a testament to the idea that even the smallest, faintest objects can hold profound secrets waiting to be uncovered. And as our technology and understanding continue to improve, we may one day unlock the full story of these mysterious celestial bodies, revealing their true nature and their place in the grand cosmic order. Brown dwarfs challenge the very way we categorize celestial objects, existing in a realm where traditional definitions blur. They are too large to be planets, yet too small to ignite the sustained hydrogen fusion that powers stars. This fundamental ambiguity makes them one of the most perplexing objects in the cosmos. But what makes them even more intriguing is that, despite their dim glow and elusive nature, they may be far more common than we ever imagined. Some estimates suggest that for every star in the Milky Way, there may be one or more brown dwarfs hiding in the darkness, undetectable with standard telescopes. If true, this would mean that brown dwarfs play a much bigger role in shaping our galaxy than we currently realize. One of the most pressing questions in brown dwarf research is their exact formation mechanism. Do they form like stars, condensing from collapsing clouds of gas and dust? Or do they form like planets, accreting material in a protoplanetary disk? The answer is still unclear, but the evidence suggests that brown dwarfs may form through a combination of both processes. Some brown dwarfs are found in isolation, much like stars that have formed independently from their parent clouds. Others, however, have been discovered in binary or multiple systems, suggesting that some may have formed in the disks of larger stars before being ejected. The ejection hypothesis is particularly interesting because it could explain why some brown dwarfs appear to have planetary-like compositions. If a brown dwarf formed within a stellar disk, it may have accreted material similar to that of gas giant planets. This could explain why some brown dwarfs exhibit chemical signatures that do not match what we expect from traditional stellar formation models. It also raises the possibility that there could be a vast population of free-floating brown dwarfs that were once part of star systems but were thrown out due to gravitational interactions. Another fascinating aspect of brown dwarfs is their magnetic activity. Despite their lack of sustained nuclear fusion, some brown dwarfs exhibit surprisingly strong magnetic fields, even stronger than those of certain low-mass stars. These magnetic fields can produce auroras similar to those seen on gas giants like Jupiter, but on a much larger scale. Observations of these auroras suggest that brown dwarfs may have dynamic magnetospheres, possibly driven by internal convection or interactions with unseen companions. The presence of strong magnetic fields also has implications for the atmospheres of brown dwarfs. Some brown dwarfs exhibit periodic radio emissions, which may be caused by charged particles interacting with their magnetic fields. This is similar to the process that creates radio waves from Jupiter's magnetosphere, suggesting that brown dwarfs may have magnetically driven weather patterns that are unlike anything we see on stars or planets. The study of brown dwarfs is also helping astronomers refine their understanding of exoplanet atmospheres. Because brown dwarfs share many characteristics with gas giants, studying their atmospheric compositions can provide insights into the conditions that may exist on exoplanets. Some brown dwarfs have been found with water vapor, methane, and even complex cloud structures, hinting at the possibility of similarly diverse atmospheres on distant exoplanets. One of the biggest challenges in studying brown dwarfs is their low luminosity. Unlike stars, which emit steady light due to nuclear fusion, brown dwarfs rely solely on residual heat from their formation. This means they become progressively dimmer as they age, making older brown dwarfs especially difficult to detect. However, recent advancements in infrared astronomy have allowed astronomers to find brown dwarfs that were previously invisible to optical telescopes. The James Webb Space Telescope, JWST, is expected to revolutionize our understanding of brown dwarfs by providing detailed infrared observations of their atmospheres, compositions, and temperatures. By analyzing the light spectra of these objects, scientists will be able to determine the precise chemical makeup of brown dwarf atmospheres, helping to answer questions about their formation and evolution. Another unresolved mystery is the temperature range of brown dwarfs. Traditionally, brown dwarfs have been classified into spectral types based on their temperatures, with the hottest brown dwarfs resembling cool stars and the coldest ones resembling gas giant planets. However, some brown dwarfs have been found with temperatures lower than expected, challenging current models of their thermal evolution. Some of these ultra-cool brown dwarfs, known as white dwarfs, have temperatures comparable to those of Earth's polar regions, raising the question of whether they might have surface conditions that allow for exotic forms of chemistry. The possibility of habitability around brown dwarfs is another area of speculation. While brown dwarfs themselves do not produce enough energy to support life as we know it, some scientists have considered whether exoplanets orbiting brown dwarfs could maintain habitable conditions. Because brown dwarfs emit infrared radiation, planets in close orbits might receive enough heat to sustain liquid water. However, the challenge is that brown dwarfs cool over time, meaning any habitable zone would shift inward as the brown dwarf ages, potentially making long-term habitability difficult. Despite these challenges, some researchers have proposed that life could exist in subsurface oceans on exoplanets orbiting brown dwarfs, similar to the way life may exist beneath the icy crusts of moons like Europa and Enceladus in our own solar system. If this is the case, then brown dwarfs could host an entirely new class of habitable worlds that operate under conditions very different from those of Earth-like planets around Sun-like stars. The search for brown dwarfs continues to push the boundaries of observational astronomy. New sky surveys are constantly uncovering previously unknown brown dwarfs, and each discovery brings new surprises. Some brown dwarfs appear to be moving at unusually high velocities, suggesting they may have been ejected from their birth environments by powerful gravitational interactions. Others exhibit strange spectral features that defy classification, hinting at exotic atmospheric processes that we have yet to fully understand. One of the most significant recent discoveries was a brown dwarf that appears to be part of a triple system, orbiting two other brown dwarfs. This system challenges our understanding of how multiple star-like objects can form and remain gravitationally bound. If brown dwarfs can form stable multi-object systems, then they may be able to host planetary systems in ways we never expected. There is also the possibility that brown dwarfs could serve as stepping stones in the formation of true stars. Some theoretical models suggest that under certain conditions, brown dwarfs could accumulate additional mass over time, eventually crossing the threshold needed to sustain nuclear fusion. If this process occurs, then brown dwarfs might not be as static as we currently believe, but rather evolving objects that exist in a continuous spectrum with low-mass stars. Brown dwarfs challenge our understanding of what it means to be a star or a planet. They exist in a liminal space, blurring the lines between these two categories and forcing us to reconsider the very definitions we use to classify celestial objects. They may not shine brightly like stars, but their mysteries illuminate new pathways for understanding the universe. As we continue to explore these enigmatic objects, we are likely to uncover even more surprises. Whether through future space telescopes, improved ground-based observations, or theoretical breakthroughs, brown dwarfs will remain one of the most fascinating subjects in modern astrophysics. They remind us that the universe is not as simple as we once thought, and that even in the darkest corners of space, there is still so much left to discover. Brown dwarfs are not just astronomical oddities. They may hold the key to understanding some of the biggest questions in astrophysics. From their origins to their compositions, these enigmatic objects continuously challenge our models of planetary and stellar evolution. As we develop more advanced observational techniques, the true nature of brown dwarfs may finally be revealed, and with that revelation could come entirely new insights into the structure of the universe. One of the most intriguing aspects of brown dwarfs is their potential role in the so-called stellar graveyard. While stars end their lives in dramatic ways, some explode as supernovae, others collapse into white dwarfs, neutron stars, or black holes. Brown dwarfs never experience such a fate. Instead, they simply fade away, growing colder and dimmer over time. This raises a fascinating question. Could ancient brown dwarfs be lurking throughout the galaxy, invisible to our current telescopes? If they do exist, they could be remnants of the earliest stages of star formation in the Milky Way, possibly holding clues about the galaxy's origins. The search for these dark, brown dwarfs has led to the discovery of an entirely new class of objects, rogue planets. These are planetary mass objects floating freely in space, not bound to any star. Some of these rogue planets share characteristics with brown dwarfs, leading scientists to wonder whether there is a continuum between the two. Could some brown dwarfs actually be former rogue planets that have gained mass over time? Or could rogue planets be failed brown dwarfs that never quite reached the mass threshold to enter that category? The boundary between these classifications is still a matter of debate, but one thing is clear: brown dwarfs do not fit neatly into the boxes we have created for them. Another compelling mystery is the presence of weather on brown dwarfs. Unlike stars, which have relatively stable surfaces, brown dwarfs have dynamic atmospheres filled with storms, clouds, and temperature fluctuations. Some brown dwarfs exhibit variability in their brightness, suggesting that massive storms, similar to Jupiter's Great Red Spot but on a much larger scale, are swirling through their upper layers. These storms can last for years, possibly even centuries, and they may be driven by complex interactions between convection currents and magnetic fields. The idea that brown dwarfs experience seasons or climate shifts is still under investigation, but it suggests that these objects are more dynamic than previously thought. The study of brown dwarf atmospheres is crucial not only for understanding these objects themselves but also for improving our knowledge of exoplanets. Many of the same techniques used to analyze brown dwarfs, such as spectroscopy and infrared imaging, are also applied to studying distant exoplanets. Because brown dwarfs are easier to observe than planets orbiting bright stars, they serve as excellent test cases for refining these observational methods. If we can accurately determine the composition and weather patterns of brown dwarfs, we will be better equipped to analyze exoplanets in the future. One of the strangest discoveries related to brown dwarfs is that some of them may have rings, similar to Saturn's but on a much larger scale. These rings, if confirmed, could be composed of dust and ice, potentially forming miniature planetary systems around the brown dwarf. The presence of rings would indicate that brown dwarfs may host their own complex environments, complete with orbiting moons or debris fields. If true, this would make brown dwarfs even more similar to planets than previously thought, further blurring the line between planetary and stellar objects. Brown dwarfs also raise questions about dark matter, the mysterious substance that makes up most of the mass in the universe. Some early theories suggested that brown dwarfs could be a significant component of dark matter, since they are difficult to detect and could exist in vast numbers. However, modern studies indicate that while brown dwarfs are numerous, they are not abundant enough to account for dark matter's gravitational effects. Even so, their presence in large numbers hints at a hidden population of celestial objects that we have yet to fully understand. The biggest question, however, remains their formation. Brown dwarfs may form like stars, collapsing from interstellar gas clouds, but they may also form like planets, accreting material in a disk. If both mechanisms are possible, then brown dwarfs represent an intersection between two fundamentally different formation processes. Understanding their origins could reshape our entire classification system for celestial bodies, forcing astronomers to rethink what it truly means to be a star or a planet. Future missions, such as the continued study of brown dwarfs with the James Webb Space Telescope, may finally provide answers to these mysteries. With improved infrared capabilities, astronomers will be able to peer deeper into the atmospheres of these objects, searching for new chemical signatures, temperature variations, and even potential signs of exoplanetary companions. Each new discovery has the potential to challenge existing theories and reveal new aspects of the universe that were previously hidden from view. Brown dwarfs are reminders that not everything in the cosmos fits into neat categories. They exist in a gray area between stars and planets, challenging our understanding of celestial evolution and the diversity of objects in the universe. As we continue to search for them, study them, and refine our methods of detection, we may uncover even more unexpected surprises. These dim, overlooked objects may turn out to be some of the most important pieces of the cosmic puzzle, shaping our understanding of the galaxy in ways we have yet to fully grasp. Brown dwarfs remain one of the most perplexing celestial objects in the universe, challenging our understanding of stellar and planetary evolution. As we continue to uncover more about them, new questions emerge, leading to deeper investigations into their origins, characteristics, and potential connections to other cosmic phenomena. These objects are more than just failed stars or oversized planets. They exist in a unique category, forming a bridge between two vastly different kinds of celestial bodies. Their existence forces us to reconsider what it means to be a star, a planet, or something entirely different. One of the most important ongoing questions surrounding brown dwarfs is their distribution in the galaxy. Are they scattered randomly, or do they tend to form in specific regions? Studies suggest that brown dwarfs are more common in star-forming regions, often found near young stars. This raises another critical question: do brown dwarfs form independently, or are they often ejected from planetary systems? Some simulations suggest that brown dwarfs may begin as planets in a protostellar disk, only to be thrown out by gravitational interactions. If this is the case, then many brown dwarfs may have once been parts of larger systems before drifting into interstellar space. The study of brown dwarfs has also led scientists to examine their potential for hosting planetary systems of their own. Given that brown dwarfs share characteristics with both stars and gas giant planets, it is reasonable to consider whether they could have their own orbiting worlds. In recent years, astronomers have indeed discovered exoplanets orbiting brown dwarfs, proving that these objects can act as miniature solar systems. However, the conditions on such planets would be vastly different from those around main sequence stars. With a brown dwarf as a host, these planets would likely experience extreme cold, little to no visible light, and potentially violent radiation bursts from their parent body. The possibility of habitable planets around brown dwarfs is another topic of great interest. Could life exist in such an environment? While the extreme conditions may seem inhospitable, some scientists argue that life could theoretically arise on moons orbiting gas giant planets within the brown dwarf system. If a gas giant were located in the habitable zone around a brown dwarf, and it had a large moon with a thick atmosphere, the conditions could potentially support liquid water. While this is purely hypothetical, it expands our understanding of the diverse places in the universe where life could possibly emerge. Another mystery surrounding brown dwarfs is their magnetic activity. Despite lacking the internal nuclear fusion that powers traditional stars, brown dwarfs still exhibit strong magnetic fields. Some have been observed emitting radio waves, similar to pulsars. This is unexpected because strong magnetic activity is typically associated with the presence of a rotating, convective core, which is common in stars but not in substellar objects. The discovery that brown dwarfs can produce auroras, much like those on Jupiter, suggests that their magnetic interactions are more complex than we previously thought. Understanding these magnetic fields could provide key insights into their internal structures and the processes occurring within them. Brown dwarfs also challenge our understanding of how atmospheres behave under extreme conditions. Their atmospheres contain complex chemistry, including molecules such as methane, ammonia, and water vapor. The presence of these compounds varies depending on the temperature and age of the brown dwarf. As they cool over time, their atmospheric composition changes, much like how a planet's atmosphere evolves. Studying these changes can give us clues about how gas giant planets develop and age, particularly exoplanets that orbit distant stars. The temperature ranges of brown dwarfs also make them valuable targets for infrared astronomy. Because they do not emit much visible light, they are best studied in the infrared spectrum, which allows scientists to detect faint heat signatures. This has led to the discovery of some of the coldest known brown dwarfs, which have surface temperatures only slightly higher than those of Earth. Some of these ultracool brown dwarfs are so cold that they might even have clouds of water or ice in their atmospheres, a phenomenon that would be unprecedented outside of planetary atmospheres. One of the biggest challenges in studying brown dwarfs is their detection. Unlike bright stars, which shine across vast distances, brown dwarfs emit only faint infrared radiation, making them difficult to spot against the backdrop of space. Many brown dwarfs have been discovered through sky surveys using specialized infrared telescopes, such as NASA's Wide Field Infrared Survey Explorer, WISE. As technology advances, new methods of detection may reveal even more of these elusive objects, potentially uncovering populations of brown dwarfs that have remained hidden until now. The role of brown dwarfs in galactic evolution is another area of growing interest. While they do not contribute significantly to stellar fusion processes, they may play a role in redistributing matter and energy within star-forming regions. Their gravitational interactions with surrounding gas clouds could influence the formation of stars and planetary systems, acting as disruptors or facilitators in the birth of new celestial bodies. Understanding their role in these processes could provide a more complete picture of how galaxies evolve over time. Brown dwarfs also hold implications for dark matter research. While it is now understood that they do not make up a significant portion of dark matter, their elusive nature raises questions about whether other, even more mysterious objects exist in the cosmos. If brown dwarfs can exist undetected in large numbers, could there be other, even fainter objects that we have yet to discover? The search for brown dwarfs may inadvertently lead to the discovery of new, previously unknown celestial phenomena. Future missions, such as those involving next-generation space telescopes, will continue to explore brown dwarfs in greater detail. The James Webb Space Telescope, with its advanced infrared capabilities, has already begun providing new insights into the atmospheres and compositions of these objects. Upcoming missions and ground-based observatories will likely uncover even more details, helping to refine our understanding of where brown dwarfs fit within the cosmic landscape. Ultimately, brown dwarfs remain one of the most intriguing and least understood types of celestial objects in the universe. They challenge our definitions of stars and planets, blur the lines between different categories of astronomical bodies, and raise fundamental questions about how objects form and evolve in space. As our observational techniques improve and our understanding deepens, these enigmatic objects may provide answers to some of the most profound mysteries in astrophysics. For now, they remain celestial enigmas, drifting through the darkness, waiting for us to uncover their secrets. Brown dwarfs continue to be a source of fascination for astronomers because they defy simple classification. They are too small to sustain hydrogen fusion like stars but too massive to be considered typical planets. This in-between status forces us to rethink our understanding of celestial objects and how they evolve over time. The study of brown dwarfs has profound implications for fields ranging from planetary science to galactic structure, and as technology advances, we are only beginning to scratch the surface of their mysteries. One of the most intriguing aspects of brown dwarfs is their formation. Unlike stars, which form from the gravitational collapse of a dense cloud of gas and dust, brown dwarfs do not gain enough mass to ignite sustained nuclear fusion. But how do they reach their final size? There are multiple theories regarding their formation. Some scientists believe that brown dwarfs form in the same way as low-mass stars but simply fail to accumulate enough mass to sustain nuclear fusion. Others suggest that they are ejected from planetary systems, forming as massive gas giant planets before being flung into interstellar space due to gravitational interactions with larger planets or stars. If this theory is correct, then many brown dwarfs may have originally formed within planetary disks, meaning they could have shared origins with exoplanets before being cast adrift. The fact that brown dwarfs exist in a mass range that overlaps with giant exoplanets adds another layer of complexity. Some of the most massive exoplanets blur the line between what is considered a planet and what is considered a brown dwarf. The distinction between the two is based largely on their formation process rather than their mass alone. But without directly observing the formation of each object, it can be difficult to categorize them definitively. This has led to debates within the scientific community about whether some exoplanets are actually brown dwarfs, and whether certain brown dwarfs could have formed as planets. The classification of brown dwarfs is further complicated by their unique spectral types. Unlike stars, which are primarily classified as O, B, A, F, G, K, or M based on their temperature and spectral characteristics, brown dwarfs have their own categories, L, T, and Y. L-type brown dwarfs are the hottest, showing signs of metal oxides and clouds in their atmospheres. T-type brown dwarfs are cooler and exhibit strong methane absorption, similar to gas giant planets like Jupiter. The coldest category, Y-type brown dwarfs, have temperatures low enough that their atmospheres may contain water clouds and other molecules typically found on planets rather than stars. The existence of Y-type brown dwarfs raises an interesting possibility. Could there be even colder, more planet-like objects still undiscovered? If brown dwarfs can exist with temperatures similar to Earth's, they may be hiding in large numbers throughout the galaxy, undetectable except in the infrared spectrum. Some scientists speculate that there may be a population of extremely cold, planet-sized brown dwarfs drifting through interstellar space, effectively making them orphan planets, or rogue planets, that never formed around a star. The discovery of more Y dwarfs could provide insight into the lower limits of star formation and help us refine our definitions of what constitutes a planet versus a star. Brown dwarfs also play a role in our understanding of stellar evolution. Because they do not undergo sustained fusion, they cool and fade over time, making them useful benchmarks for studying how stars evolve at their lowest mass limits. By observing brown dwarfs of different ages, astronomers can track how their luminosity, temperature, and spectral characteristics change over billions of years. This information helps refine models of both stellar and planetary evolution, as brown dwarfs exist in an overlapping category that connects the two. One of the most puzzling aspects of brown dwarfs is their internal structure. Unlike stars, which have fusion-powered cores, and planets, which are primarily differentiated with solid or liquid interiors, brown dwarfs are thought to have convective interiors where heat is transported outward through turbulent motion. This lack of a well-defined core creates unusual behaviors, including complex atmospheric dynamics. Some brown dwarfs exhibit weather patterns with massive, Jupiter-like storms that circulate across their surfaces. Others have cloud structures that change over time, suggesting that their atmospheres may be far more active than previously assumed. Another major area of research involves the magnetic activity of brown dwarfs. Despite lacking the strong nuclear reactions that power stars, some brown dwarfs generate intense magnetic fields. Observations have shown that certain brown dwarfs produce powerful radio emissions, similar to pulsars. This unexpected behavior challenges our understanding of how magnetic fields are generated in celestial bodies. On planets like Earth and Jupiter, magnetic fields are created by the movement of conductive material in their interiors. If brown dwarfs lack the same type of internal dynamo as planets, then what mechanism is responsible for their magnetism? Studying these magnetic fields could provide crucial insights into both stellar and planetary magnetism, offering a new perspective on how celestial bodies generate and maintain their magnetic properties. One of the most exciting developments in the study of brown dwarfs is the potential discovery of exoplanets orbiting them. Until recently, it was unclear whether brown dwarfs could host planetary systems, but advances in exoplanet detection have revealed that they can indeed have orbiting planets. However, these planetary systems differ significantly from those around main-sequence stars. Because brown dwarfs do not emit much visible light, any planets orbiting them would experience extremely dim conditions, with only infrared radiation providing warmth. This has led scientists to question whether life could exist in such an environment. While the surface conditions of planets around brown dwarfs would likely be harsh, it is possible that subsurface oceans, similar to those found on moons like Europa and Enceladus, could provide a stable environment for life. The discovery of planets around brown dwarfs also raises questions about their formation history. Did these planets form alongside the brown dwarf in a miniature solar system, or were they captured later? If brown dwarfs can form planetary systems similar to stars, this could mean that planetary formation is far more common than previously believed, occurring even in environments that lack a traditional host star. Brown dwarfs also provide valuable insights into the early universe. Because they do not undergo the same rapid fusion processes as stars, their compositions reflect the original materials present in their formation regions. By studying the elemental abundances in brown dwarfs, scientists can learn more about the chemical evolution of galaxies and the conditions that existed in the early cosmos. One of the biggest challenges in studying brown dwarfs is their sheer faintness. Because they emit little visible light, they are incredibly difficult to detect with traditional telescopes. Many brown dwarfs have only been discovered through infrared sky surveys, such as NASA's Wide Field Infrared Survey Explorer, WISE. As observational technology improves, new brown dwarfs are being found at an increasing rate, leading to the possibility that there are many more hidden in the galaxy than we currently know. Some estimates suggest that brown dwarfs could be nearly as numerous as stars, forming a vast, invisible population of objects scattered throughout the Milky Way. In the coming years, the study of brown dwarfs is expected to accelerate with the help of advanced telescopes like the James Webb Space Telescope. With its powerful infrared capabilities, Webb is capable of detecting fainter and colder brown dwarfs than ever before, shedding light on their atmospheric compositions, temperatures, and potential planetary systems. Future missions may even allow for direct imaging of brown dwarf atmospheres, revealing cloud patterns, weather systems, and potentially even auroras similar to those seen on Jupiter. Ultimately, brown dwarfs challenge many of our preconceived notions about celestial objects. They exist in a liminal space between stars and planets, defying easy classification and forcing astronomers to reconsider their definitions. As new discoveries are made, brown dwarfs may reveal hidden aspects of the universe that we have yet to even imagine. They are the cosmic nomads of the universe, drifting, cooling, and holding secrets that we are only just beginning to uncover. Brown dwarfs represent an astronomical paradox, a bridge between the realms of stars and planets, yet belonging fully to either. Their presence in the cosmos challenges the traditional categories we use to define celestial objects, making them some of the most enigmatic and compelling bodies to study. As we continue to probe the mysteries of these failed stars, we find that they hold the potential to reshape our understanding of not only planetary and stellar evolution, but also the fundamental nature of the universe itself. One of the most profound questions surrounding brown dwarfs is their true abundance. Because they emit so little visible light, they are incredibly difficult to detect, which means that our current estimates of their population might be far too low. If brown dwarfs are as common as some models predict, they could make up a significant portion of the missing mass in the Milky Way, perhaps even playing a role in the ongoing mystery of dark matter. While brown dwarfs themselves do not account for the entirety of dark matter, their widespread presence could hint at other hidden populations of celestial objects that remain undetected. Another fascinating aspect of brown dwarfs is their relationship with rogue planets. Unlike brown dwarfs, which form through the collapse of a gas cloud but fail to ignite fusion, rogue planets are thought to be planets that were ejected from their original solar systems. However, as observational techniques improve, scientists have found objects that blur the line between brown dwarfs and rogue planets, making it difficult to classify them. If a planet-like object forms in isolation, is it a brown dwarf, or is it simply a planet that never found a star? This ambiguity complicates our understanding of planetary formation and suggests that the universe is far more chaotic in its structure than we previously believed. Brown dwarfs also raise intriguing possibilities about the potential for exotic forms of life. While most discussions of habitability focus on planets orbiting stable main-sequence stars, brown dwarfs introduce a new variable, infrared radiation. Unlike the Sun, which emits a broad spectrum of light, brown dwarfs primarily radiate in the infrared range. This means that any planets orbiting them would experience a very different type of illumination, one that could potentially support unique biological processes. Some scientists have speculated that life forms on such planets might evolve to use infrared vision instead of visible light, leading to entirely different evolutionary pathways than those found on Earth. The question of whether brown dwarfs can support life is further complicated by their instability. Unlike main-sequence stars, which can shine steadily for billions of years, brown dwarfs gradually cool over time. This means that any habitable zone around a brown dwarf is temporary. Eventually, the object will become too cold to support liquid water on any orbiting planets. However, even if brown dwarfs themselves are not ideal long-term hosts for life, they could still play a role in the formation and distribution of life throughout the galaxy. Some scientists have proposed that brown dwarfs, like Jupiter, could have moons with subsurface oceans heated by tidal forces rather than stellar radiation. If life exists in such environments within our own solar system, similar conditions around brown dwarfs could theoretically harbor life as well. Another mystery surrounding brown dwarfs is their magnetic activity. Traditionally, strong magnetic fields are associated with stars that undergo fusion or planets with metallic cores, yet brown dwarfs, despite lacking both, have been observed producing radio emissions and even auroras. The mechanism behind this is still poorly understood, but one possibility is that brown dwarfs have internal convective processes that generate magnetic fields in ways unlike anything seen in either stars or planets. Studying these magnetic fields could provide insights not only into brown dwarfs but also into planetary and stellar magnetism as a whole. Because brown dwarfs exist in such a liminal space between stars and planets, they also challenge our definitions of planetary system formation. The discovery of planets orbiting brown dwarfs suggests that even objects incapable of sustained nuclear fusion can have their own planetary systems, further blurring the distinction between stars and large planets. Some brown dwarfs have been found with disk structures similar to those seen around young stars, implying that they can form planets in the same way that main-sequence stars do. If planetary formation can occur even around failed stars, it raises the possibility that planets might be far more common throughout the universe than we previously thought. The cooling process of brown dwarfs is another area of active research. Unlike stars, which maintain a relatively stable temperature due to ongoing nuclear reactions, brown dwarfs gradually cool over time, transitioning from hotter L-type objects to cooler Y-type objects. This cooling process allows astronomers to use brown dwarfs as cosmic thermometers, helping to estimate the ages of various stellar populations in the galaxy. By studying how quickly brown dwarfs cool, scientists can develop models that help determine the age of star clusters and even refine estimates for the age of the Milky Way itself. Observations of brown dwarfs have also challenged long-held assumptions about how objects of different sizes behave. Some brown dwarfs exhibit rapid rotation rates, spinning much faster than expected for objects of their mass. This rapid rotation affects their atmospheric dynamics, leading to extreme weather patterns and cloud formations. Some brown dwarfs have even been observed with changing light curves, indicating shifting cloud cover or storms that could rival the Great Red Spot on Jupiter. These atmospheric dynamics provide an invaluable window into how weather patterns operate on objects that are neither fully planetary nor fully stellar. Despite all we have learned about brown dwarfs, many unanswered questions remain. One of the biggest mysteries is whether the coldest Y-type brown dwarfs represent the true lower limit of stellar-like objects, or if even colder, more planet-like objects exist in interstellar space. If brown dwarfs can exist with temperatures close to that of Earth, it could suggest that the boundary between brown dwarfs and rogue planets is even more blurred than we currently understand. Future missions will be crucial in unlocking more of these mysteries. The James Webb Space Telescope, with its advanced infrared capabilities, is expected to revolutionize our understanding of brown dwarfs by detecting even fainter and colder specimens. Additionally, upcoming ground-based telescopes, such as the Extremely Large Telescope, ELT, will provide higher-resolution observations of brown dwarf atmospheres, helping to unravel their complex weather patterns and compositions. As our ability to detect and study brown dwarfs improves, these mysterious objects will likely force us to rethink many aspects of astrophysics. They challenge our definitions of what it means to be a star or a planet, blur the lines between planetary systems and stellar remnants, and offer tantalizing hints about unseen populations of objects lurking in the cosmos. Whether they are failed stars, giant rogue planets, or something entirely different, brown dwarfs remain one of the most intriguing and mysterious classes of objects in the universe. Brown dwarfs continue to defy easy classification, making them some of the most compelling objects in astrophysics. One of the greatest ongoing debates about them revolves around their formation. Traditionally, objects in space form through two primary mechanisms. Stars form from the gravitational collapse of gas clouds, while planets form from the accretion of material in a protoplanetary disk. But brown dwarfs don't fit neatly into either category. Some brown dwarfs appear to have formed like stars, collapsing directly from a gas cloud without the necessary mass to ignite fusion. Others show signs of forming within protoplanetary disks, much like massive planets. This dual nature raises the question, are brown dwarfs more like failed stars, or are they simply planets that grew too large? If brown dwarfs form like stars, then their properties should resemble those of low-mass stars, with similar distributions in stellar clusters. If they form like planets, then they might be expected to be found in orbit around larger stars or brown dwarfs, rather than as isolated objects. Observations suggest that both formation pathways may be possible, meaning that brown dwarf could be a catch-all term for objects with vastly different origins. This challenges astronomers to rethink not just how we classify these objects, but how we classify celestial bodies as a whole. Another mystery concerns the atmospheres of brown dwarfs. Because they do not undergo sustained fusion, their atmospheres cool and change over time, much like those of gas giant planets. Some brown dwarfs have been observed with thick cloud layers composed of exotic materials such as silicates and iron droplets, clouds that would be completely alien in a typical planetary or stellar atmosphere. These clouds can shift and disperse, leading to dramatic fluctuations in brightness as different atmospheric layers come into view. This variability suggests that brown dwarfs experience turbulent weather patterns on a massive scale, far beyond anything seen in our solar system. The weather on brown dwarfs is particularly intriguing because it could serve as a model for exoplanet atmospheres. Many gas giants outside our solar system orbit close to their stars, experiencing extreme heat and violent storms. studying brown dwarfs, which exist in isolation, allows astronomers to examine atmospheric processes without interference from a nearby star. This could provide insights into the nature of gas giant exoplanets, helping us understand their weather systems, cloud formation, and even potential habitability. One of the strangest findings about brown dwarfs is their surprising ability to generate auroras. On Earth, auroras occur when charged particles from the Sun interact with our planet's magnetic field. Jupiter has auroras as well, generated by its strong magnetic field and interactions with its moons. But brown dwarfs do not have a strong solar wind or close-in moons, so their auroras must be created through a different mechanism. The fact that they produce powerful radio emissions suggests that their magnetic fields are far more complex than previously thought. Understanding how brown dwarfs generate these magnetic fields could provide insights into magnetism and other celestial bodies, including planets, stars, and even neutron stars. The temperatures of brown dwarfs also present an interesting puzzle. When first formed, brown dwarfs can be relatively hot, with temperatures of thousands of degrees, but they quickly cool down over time. The coldest known brown dwarfs, classified as white dwarfs, can have surface temperatures comparable to those of Earth, or even below the freezing point of water. This challenges the traditional idea that all celestial bodies must be either hot, like stars, or cold, like planets. Instead, brown dwarfs occupy a middle ground, showing that objects in space can cool dramatically over time while still retaining some stellar properties. Despite their cool temperatures, brown dwarfs can still emit significant amounts of infrared radiation. This is due to their internal heat, which slowly escapes over billions of years. Infrared telescopes, such as the James Webb Space Telescope, are particularly well suited to studying brown dwarfs, as they can detect even the faintest heat signatures. Future observations with these advanced instruments could reveal new classes of brown dwarfs, possibly even colder ones that blur the line between planets and failed stars even further. Brown dwarfs also challenge our understanding of planetary system architecture. Some brown dwarfs have been discovered with planets or planetary mass companions, raising questions about how these systems form. If brown dwarfs can host planets, does that mean they should be considered stars, even if they lack fusion? Or are they simply oversized planets that happen to have smaller planets orbiting them? The existence of planetary systems around brown dwarfs suggests that planet formation is an extremely flexible process, capable of occurring under a wide range of conditions. Another intriguing possibility is that some brown dwarfs could have formed in binary star systems before being ejected due to gravitational interactions. If this is the case, then many of the isolated brown dwarfs we observe today may have originally been part of larger systems. This raises the possibility that there are many more hidden brown dwarfs, ones that are still bound to stars but are difficult to detect because of their faintness. The discovery of free-floating brown dwarfs, which drift through space unattached to any star, adds another layer to their mystery. These rogue brown dwarfs could be remnants of failed star formation, or they could have been ejected from their original systems due to gravitational interactions with larger objects. Some of these free-floating brown dwarfs have been found at surprisingly close distances to Earth, suggesting that they may be far more common than previously thought. If brown dwarfs are numerous in our galaxy, they could represent an important component of the Milky Way's overall mass and structure. Even though brown dwarfs are difficult to detect, they could hold the key to understanding one of the biggest mysteries in cosmology: dark matter. While brown dwarfs themselves are not considered a major component of dark matter, their abundance could hint at the existence of other unseen objects. If brown dwarfs are more numerous than expected, then other faint, non-luminous objects could also exist in large numbers, helping to account for some of the missing mass in the universe. As we continue to study brown dwarfs, we may find that they challenge not just our understanding of stars and planets, but of the universe itself. Their strange properties, unusual atmospheres, and complex magnetic fields make them some of the most enigmatic objects in space. With upcoming advancements in telescope technology, we are on the brink of uncovering even more about these cosmic oddities. As we probe deeper into their mysteries, brown dwarfs may force us to rethink fundamental concepts about how objects in space form, evolve, and interact. Brown dwarfs are more than just failed stars. They may hold the key to some of the deepest mysteries in astrophysics. One of the biggest unresolved questions about them is how many exist in our galaxy. Because they do not shine brightly like stars, they are extremely difficult to detect. The most effective way to find them is through infrared telescopes, which can pick up their faint heat signatures. However, even with advanced instruments, we have likely only scratched the surface of the brown dwarf population. Some studies suggest that for every star in the Milky Way, there could be several brown dwarfs lurking in the darkness, unseen and unaccounted for. If true, this means that brown dwarfs could be one of the most common types of celestial objects in the universe. The potential abundance of brown dwarfs raises fascinating questions about their role in the galaxy. If they are as numerous as some predictions suggest, they could play a major role in the overall structure of the Milky Way. Their combined mass could contribute significantly to the gravitational balance of the galaxy, affecting everything from the motion of stars to the distribution of interstellar gas. Some even speculate that brown dwarfs could make up part of the missing, dark matter that astronomers have struggled to explain for decades. While brown dwarfs themselves are not completely invisible, their faint nature means that if they exist in vast numbers, they could add up to a significant portion of the unseen mass in the universe. Another mystery surrounding brown dwarfs is their magnetic fields. In stars like the Sun, magnetic fields are generated by the movement of hot, ionized gas. In planets like Earth and Jupiter, magnetic fields are produced by the motion of liquid metal deep inside their cores. But brown dwarfs do not have the same internal conditions as other stars or planets. Despite this, they have been observed producing powerful radio emissions, suggesting the presence of strong magnetic fields. Some brown dwarfs even exhibit auroras, much like those seen on Jupiter and Earth. This is particularly strange because auroras are usually caused by interactions with a solar wind, something brown dwarfs do not have. The presence of auroras on brown dwarfs suggests that their magnetic fields may be interacting with interstellar particles or even with unseen planetary companions. The weather on brown dwarfs is another area of active research. Because they are too small to sustain hydrogen fusion, brown dwarfs cool down over time, allowing their atmospheres to change in ways that are very different from those of stars. Observations suggest that brown dwarfs have dynamic and sometimes violent weather systems, with massive cloud formations that can shift and evolve over short timescales. Some brown dwarfs show dramatic variations in brightness, which scientists believe could be caused by giant storms or changing cloud coverage. These storms may be similar to the Great Red Spot on Jupiter but on an even larger scale, covering entire hemispheres of the brown dwarf. Understanding the atmospheres of brown dwarfs is not just about studying them in isolation. It also has important implications for exoplanet research. Many gas giant exoplanets orbit their stars at close distances, experiencing extreme heat and intense radiation. Brown dwarfs, which exist in the cold depths of space, offer a natural laboratory for studying planetary atmospheres without the interference of a nearby star. By comparing brown dwarf atmospheres to those of exoplanets, scientists can learn more about how clouds, storms, and temperature variations affect giant planets outside our solar system. One of the biggest surprises in brown dwarf research has been the discovery of white dwarfs, the coldest known type of brown dwarf. Some white dwarfs have surface temperatures comparable to those of Earth, with estimates ranging from room temperature to below the freezing point of water. This challenges our traditional view of celestial objects, as we typically think of space as a place filled with either blazing hot stars or frigid, icy planets. Brown dwarfs show that there is a middle ground, objects that are neither fully stars nor fully planets, but something in between. The existence of cold brown dwarfs also raises the possibility that there may be even colder objects still waiting to be discovered, possibly ones that blur the line between gas giants and brown dwarfs even further. The discovery of free-floating brown dwarfs, ones that do not orbit any star, has also led to new questions about their origins. Some of these rogue brown dwarfs may have formed in isolation, but others could have been ejected from young star systems due to gravitational interactions. If this is true, then it means that planetary systems may be far more chaotic than we once thought, with objects frequently being thrown out into interstellar space. Some free-floating brown dwarfs have even been found at relatively close distances to Earth, suggesting that they could be far more common than previously believed. If our solar system had formed in a more crowded environment, it is possible that it could have ejected brown dwarfs of its own. Some scientists have proposed that there may be a population of undetected brown dwarfs lurking in the outer reaches of our own solar system. While no such object has been found yet, the idea remains intriguing. A brown dwarf in the farthest parts of our solar system would be extremely difficult to detect, but it could explain some of the unexplained gravitational anomalies observed in the orbits of distant objects. If a brown dwarf were lurking beyond Pluto, it could reshape our understanding of the solar system's outermost regions. Brown dwarfs also provide clues about the earliest stages of star formation. By studying young brown dwarfs, astronomers can learn more about how gas clouds collapse and form new celestial objects. Some brown dwarfs have been found with disks of gas and dust around them, similar to the protoplanetary disks seen around young stars. This raises the possibility that brown dwarfs could form their own planetary systems, further blurring the line between small stars and large planets. If brown dwarfs can host planets, then the definition of what constitutes a star or a planet becomes even more complicated. Another unresolved question is whether brown dwarfs could ever ignite fusion under the right conditions. While most brown dwarfs are thought to be permanently stuck below the fusion threshold, some models suggest that certain brown dwarfs might gain enough mass over time, possibly through collisions or accretion, to briefly ignite hydrogen fusion. If this is the case, then some brown dwarfs might not be failed stars at all, but rather stars that took an unusually long time to begin shining. The search for brown dwarfs is far from over. With upcoming telescope missions, including more powerful infrared observatories, scientists expect to find many more of these elusive objects. Future discoveries could reshape our understanding of how stars and planets form, how magnetic fields work in space, and how common objects like brown dwarfs truly are in the universe. Brown dwarfs may not be as bright as stars, but their mysteries shine just as brightly in the minds of astronomers. The more we learn about them, the more they challenge our understanding of what it means to be a star, a planet, or something in between. As we continue to explore the universe, brown dwarfs stand as a reminder that space is full of surprises, waiting to be uncovered. One of the most perplexing aspects of brown dwarfs is their internal structure. Unlike stars, which have nuclear fusion to counteract the force of gravity, brown dwarfs rely entirely on something called electron degeneracy pressure. This is a quantum mechanical effect that prevents the atoms inside a brown dwarf from collapsing further. Essentially, the electrons inside the object push against each other, creating a stabilizing force that stops the brown dwarf from shrinking beyond a certain point. This is the same principle that prevents white dwarfs, the remnants of dead stars, from collapsing under their own gravity. But the difference is that brown dwarfs never became full-fledged stars in the first place. Because of this unique internal structure, brown dwarfs behave in ways that defy intuition. For example, if you add mass to a brown dwarf, you might expect it to become larger, just like adding more gas to a balloon makes it expand. But instead, adding mass to a brown dwarf actually makes it shrink. This happens because the increased gravity compresses the object even further, making it denser rather than bigger. This counterintuitive behavior is one of the many ways brown dwarfs differ from both planets and stars. Another interesting consequence of electron degeneracy pressure is that all brown dwarfs, regardless of their mass, end up being roughly the same size. Whether a brown dwarf is just above the planetary threshold or close to the limit of becoming a true star, its physical diameter remains similar. This makes it difficult to distinguish between massive gas giant planets and small brown dwarfs based on size alone. Instead, scientists have to rely on other factors, such as temperature, chemical composition, and how the object emits radiation. Brown dwarfs are also incredibly long-lived. Since they do not sustain hydrogen fusion like normal stars, they do not have a fixed lifespan in the same way that stars do. Instead, brown dwarfs gradually cool over billions of years. The youngest brown dwarfs can be relatively warm, with surface temperatures exceeding thousands of degrees, but as they age, they become cooler and fainter. Some of the oldest brown dwarfs in the universe may have cooled to temperatures barely above that of deep space. This slow cooling process means that brown dwarfs can persist for an incredibly long time, potentially lasting far beyond the lifetimes of most stars. Because they evolve so slowly, brown dwarfs also serve as valuable time capsules for studying the history of the universe. By analyzing their compositions, scientists can gain insight into the conditions present in different eras of cosmic history. Some brown dwarfs may be relics from the earliest stages of the Milky Way, preserving clues about how the first stars and planets formed. Since brown dwarfs do not undergo the dramatic life cycles of stars, they provide a more stable record of their formation and evolution. One of the most exciting possibilities in brown dwarf research is the potential for discovering planets around them. While brown dwarfs are not true stars, they still have enough mass to exert a strong gravitational influence. This means that they could theoretically host their own planetary systems, much like regular stars do. In fact, some brown dwarfs have already been found with orbiting planets, challenging our understanding of how planetary systems form. The presence of planets around brown dwarfs raises intriguing questions about the potential for habitability. Since brown dwarfs do not emit significant visible light, any planets orbiting them would exist in perpetual twilight or near total darkness. However, if a planet were close enough to its brown dwarf host, it could still receive enough heat to sustain liquid water. Some researchers have speculated that under the right conditions, a planet orbiting a brown dwarf could potentially support life, though it would be very different from life as we know it on Earth. The atmospheres of brown dwarfs themselves also provide valuable insights for astrobiology. Many brown dwarfs exhibit complex atmospheric chemistry, with elements like methane, water vapor, and ammonia present in their clouds. These same compounds are key markers in the search for life on exoplanets. By studying brown dwarf atmospheres, scientists can refine their techniques for detecting biosignatures on distant worlds. In a way, brown dwarfs act as natural laboratories for testing the methods that will one day be used to find alien life. One of the most puzzling discoveries about brown dwarfs is the presence of unexpected weather patterns. Observations have revealed that many brown dwarfs experience intense storms, with cloud formations shifting over time. Some show periodic brightness variations, suggesting that massive cloud systems are rotating in and out of view. These weather patterns may be driven by complex atmospheric dynamics, similar to those seen on gas giant planets. However, the exact mechanisms behind brown dwarf weather remain a subject of ongoing research. Some brown dwarfs exhibit a phenomenon known as banded atmospheres, where different layers of gas move at different speeds. This is similar to the banded structure seen on Jupiter and Saturn, where jet streams create alternating belts of high and low pressure. But in the case of brown dwarfs, these bands appear to be even more extreme, with rapid winds and turbulent mixing. The presence of such intense atmospheric activity in objects that do not receive energy from a central star is a mystery that scientists are still trying to unravel. Another unsolved mystery about brown dwarfs is their formation process. While we know that stars form from collapsing clouds of gas and dust, it is unclear whether brown dwarfs form in the same way or through a different mechanism. One possibility is that brown dwarfs start out as normal stars but fail to accumulate enough mass to ignite fusion. Another possibility is that they form more like giant planets, through a process of gradual accretion. Understanding how brown dwarfs form could provide valuable insights into the broader process of star and planet formation. Recent discoveries have also hinted at the possibility of failed binary star systems, where one object in a pair becomes a normal star while the other remains a brown dwarf. These systems challenge traditional models of stellar evolution and suggest that the boundary between stars and brown dwarfs may be more fluid than previously thought. Studying these binary systems could help scientists refine their understanding of how mass and temperature determine the fate of celestial objects. As telescope technology improves, the search for brown dwarfs is becoming increasingly sophisticated. The James Webb Space Telescope, for example, is expected to revolutionize brown dwarf research by providing unprecedented infrared sensitivity. Future telescopes may even be able to directly image brown dwarf atmospheres in detail, revealing new insights about their weather, chemistry, and potential for hosting planets. Ultimately, brown dwarfs represent one of the biggest gaps in our understanding of the universe. They challenge our definitions of what it means to be a star or a planet, and they hold clues to some of the most fundamental questions in astrophysics. From their mysterious magnetic fields to their potential role in the search for extraterrestrial life, brown dwarfs continue to surprise and intrigue scientists. The more we learn about these enigmatic objects, the more we realize how much we still do not know. Brown dwarfs may not shine as brightly as stars, but their mysteries illuminate the vast and uncharted territories of the cosmos. With every new discovery, we come one step closer to understanding the true nature of these elusive celestial bodies. Brown dwarfs exist in a strange middle ground between planets and stars, but their mysteries only deepen the more we study them. One of the biggest puzzles is their magnetic activity. Despite lacking the powerful nuclear fusion that fuels stars, brown dwarfs somehow generate strong magnetic fields, sometimes even stronger than those of fully fledged stars. This defies our expectations because, in most cases, strong magnetic fields require the movement of charged particles in a hot, convective interior. But brown dwarfs, especially older and cooler ones, should lack the necessary conditions to sustain such intense magnetism. Observations have shown that some brown dwarfs produce radio emissions similar to those seen in highly active stars. These emissions suggest that brown dwarfs experience something akin to stellar flares, bursts of energy that result from the twisting and reconnecting of magnetic field lines. But since brown dwarfs do not have the same internal dynamics as stars, scientists are still unsure how exactly these magnetic fields arise. Some theories suggest that their interiors may remain turbulent enough to generate magnetic activity, while others propose that brown dwarfs may acquire their magnetic fields from interactions with nearby objects, such as planets or companion stars. These unexpected radio emissions are not just a curiosity, they provide a powerful tool for discovering brown dwarfs in the first place. Most brown dwarfs are incredibly faint, especially in visible light, making them difficult to detect. But their radio emissions can give away their presence even when they are otherwise invisible to telescopes. This method of detection has already led to the discovery of several brown dwarfs that would have otherwise gone unnoticed. It also raises the possibility that there are far more brown dwarfs in the universe than previously believed, potentially outnumbering stars in some regions of space. Another major question about brown dwarfs is their distribution throughout the galaxy. Are they more common in certain regions? Do they tend to form alone, or are they frequently found in binary or multiple systems? So far, observations suggest that brown dwarfs can be found in a variety of environments, from dense star-forming regions to the emptiest stretches of interstellar space. Some brown dwarfs have even been discovered drifting alone between stars, leading scientists to speculate that they may have been ejected from their original birthplaces. This idea, of rogue brown dwarfs wandering the galaxy, adds an extra layer of mystery to their existence. If brown dwarfs can be ejected from their birth environments, how many of them are floating unseen in the vast darkness of interstellar space? Could there be entire populations of brown dwarfs that we have yet to detect? Some scientists believe that the number of rogue brown dwarfs could be staggering, potentially rivaling or even exceeding the number of regular stars in the Milky Way. If this is the case, it would have profound implications for our understanding of galactic evolution. Brown dwarfs, despite their faintness, could play an important role in shaping the structure of the galaxy. Their gravitational influence, while small compared to massive stars, could subtly affect the motion of nearby stars and gas clouds. If brown dwarfs are more common than we think, they could even contribute to the mysterious phenomenon known as dark matter, an invisible substance that appears to make up a significant portion of the universe's total mass. While brown dwarfs are not themselves candidates for dark matter, their abundance could help explain some of the gravitational anomalies observed in galaxies. If astronomers discover that there are far more brown dwarfs than expected, it could mean that the missing mass in galaxies is partially made up of these elusive objects. This would not fully solve the dark matter mystery, but it would provide another piece of the puzzle in understanding the large-scale structure of the cosmos. Another mystery surrounding brown dwarfs is their relationship to exoplanets. Some massive exoplanets, known as superjupiters, blur the line between planets and brown dwarfs. These objects are often found orbiting stars, but their masses place them uncomfortably close to the brown dwarf range. The question is, did these objects form like planets, through the slow accretion of material in a protoplanetary disk, or did they form like brown dwarfs, through the direct collapse of a gas cloud? The distinction between a massive planet and a small brown dwarf is not just a matter of classification, it affects our understanding of how planetary systems form. If superjupiters form more like brown dwarfs, it could mean that some planetary systems develop in ways we have yet to fully understand. This would challenge existing models of planet formation and force astronomers to rethink how solar systems come together. The search for brown dwarfs has also led to the discovery of some truly bizarre objects that defy easy categorization. One example is the class of brown dwarfs known as white dwarfs, the coldest known brown dwarfs, with temperatures comparable to those of Earth's atmosphere. Some white dwarfs are so cold that they barely emit any detectable infrared radiation, making them some of the faintest objects ever discovered outside our solar system. The existence of white dwarfs raises the question, what is the lower limit for brown dwarfs? Is there a point at which an object becomes so cold and faint that it is indistinguishable from a rogue planet? If so, how many of these, invisible, brown dwarfs are lurking in the galaxy, undetectable with current technology? Some scientists have speculated that there could be a hidden population of extremely cold brown dwarfs lurking closer to the solar system than we realize. In fact, some researchers have even suggested that an undetected brown dwarf could exist in the outer reaches of the solar system itself. While no such object has been found, the idea that a nearby brown dwarf could remain undiscovered highlights just how little we know about these enigmatic objects. The mystery of brown dwarfs is far from solved. Every new discovery raises more questions than answers, and astronomers are constantly refining their theories to keep up with the latest findings. But one thing is certain, brown dwarfs challenge our understanding of the universe in ways we never expected. They exist in a realm between planets and stars, defying traditional classifications and pushing the limits of what we thought was possible. As technology advances, the search for brown dwarfs will continue to uncover new surprises. Whether they hold the key to understanding planetary formation, magnetic fields, or even the structure of the galaxy itself, brown dwarfs remain one of the most fascinating and mysterious objects in the universe. Brown dwarfs are not just scientific curiosities. They could hold the key to some of the biggest questions in astrophysics. One of the most intriguing mysteries is how they evolve over time. Unlike stars, which follow a predictable life cycle, burning hydrogen, expanding into red giants, and eventually collapsing into white dwarfs, brown dwarfs take a very different path. Without the steady energy output of nuclear fusion, their evolution is dictated purely by cooling and contraction. In the early stages of their lives, brown dwarfs can be surprisingly hot, with temperatures reaching thousands of degrees. This heat comes not from fusion, but from the gravitational energy released as they collapse from the gas clouds that formed them. Over time, however, brown dwarfs cool down, losing their internal heat as it radiates away into space. Unlike stars, which shine for billions of years, brown dwarfs gradually fade, becoming cooler and dimmer over time. This cooling process creates a fascinating situation where older brown dwarfs can be nearly indistinguishable from giant planets. A young brown dwarf might have a temperature similar to a small star, but an old brown dwarf could have a temperature close to that of Jupiter. This means that if we were to find an ancient brown dwarf drifting through space, it might look almost exactly like a planet, making classification even more difficult. This blurring of lines between planets and brown dwarfs raises another question. Could brown dwarfs eventually cool down enough to become completely undetectable? In theory, a brown dwarf that has cooled for billions of years could end up as a dark, frozen object, emitting almost no light at all. If such objects exist, they could be some of the hardest things to find in the universe, lurking unseen in the depths of space. But cooling down doesn't just change a brown dwarf's brightness, it also affects its atmosphere. Brown dwarfs are known for their complex and ever-changing weather patterns, with massive storms and turbulent cloud formations shaping their appearance. In fact, some brown dwarfs have been observed with enormous storm systems that resemble Jupiter's Great Red Spot, but on an even larger scale. As a brown dwarf cools, its atmosphere undergoes dramatic chemical changes. The hottest brown dwarfs have atmospheres dominated by hydrogen gas, much like stars, but as they cool, different molecules start to form. Intermediate temperature brown dwarfs show evidence of clouds made of iron and silicate dust, which condense out of the atmosphere in a way similar to how water clouds form on Earth. At even lower temperatures, methane becomes a major component of the atmosphere, similar to what we see on gas giant planets like Jupiter. Eventually, in the coldest brown dwarfs, water vapor clouds can form, making them even more planet-like. This progression of atmospheric changes is one of the reasons brown dwarfs are considered such important objects for understanding exoplanets. By studying brown dwarfs, astronomers can get a glimpse into what the atmospheres of gas giant exoplanets might look like under different conditions. Since many brown dwarfs are isolated in space, without the overwhelming brightness of a nearby star, they provide a much clearer view of atmospheric processes than we can get from exoplanets orbiting stars. This connection between brown dwarfs and exoplanets also brings up another question: could brown dwarfs have their own planetary systems? So far, astronomers have found several brown dwarfs with planetary companions, suggesting that some brown dwarfs do indeed form their own miniature solar systems. These planets orbiting brown dwarfs raise fascinating questions about habitability. Traditional definitions of the habitable zone, the region around a star where conditions might allow liquid water to exist, are based on the idea of a stable energy source like the Sun. But brown dwarfs are not stable sources of heat and light. Their brightness changes dramatically as they cool over time, meaning any planet in the habitable zone of a young brown dwarf would eventually freeze as the brown dwarf dims. However, some researchers have proposed that under certain conditions, planets orbiting brown dwarfs might still be able to support life. For example, if a planet had a thick atmosphere or a strong greenhouse effect, it might be able to retain enough heat to remain habitable for long periods, even as its brown dwarf cools. Additionally, tidal heating, where the gravitational pull of a brown dwarf keeps a planet's interior warm, could provide an alternative source of energy, much like how Jupiter's moon Europa has a subsurface ocean kept warm by tidal forces. Even if life as we know it cannot exist on planets orbiting brown dwarfs, these systems could still be valuable targets for future exploration. Studying how planets interact with brown dwarfs could teach us more about planetary formation and evolution in extreme environments. Beyond their atmospheres and potential planets, brown dwarfs also raise questions about how common they are in the universe. Since they are so faint and difficult to detect, astronomers suspect that we have only found a small fraction of the brown dwarfs that exist. Some estimates suggest that for every star in the Milky Way, there may be several brown dwarfs lurking in the darkness, completely unnoticed. If this is true, it means that brown dwarfs could represent a significant, yet hidden, portion of the galaxy's total mass. This could have major implications for how we understand the formation and structure of the Milky Way. If there are more brown dwarfs than we think, they could play a larger role in the galaxy's gravitational dynamics, subtly influencing the motion of stars and gas clouds over billions of years. The search for brown dwarfs continues to push the limits of our observational technology. Infrared telescopes like the James Webb Space Telescope are designed to detect faint, cool objects, making them ideal for spotting brown dwarfs that might otherwise go unnoticed. With these advanced tools, astronomers hope to map out the full population of brown dwarfs in our galaxy, revealing just how many of these mysterious objects are out there. One of the most exciting prospects is the possibility of finding a brown dwarf closer to Earth than any known star. Currently, the closest known star system is Alpha Centauri, about 4.2 light-years away. But if there are rogue brown dwarfs wandering through interstellar space, it's possible that one could be much closer, potentially within just a few light-years of the Sun. The discovery of a nearby brown dwarf would open up incredible opportunities for study. Being able to observe a brown dwarf up close would allow astronomers to analyze its atmosphere, weather patterns, and internal structure in unprecedented detail. It could also serve as a stepping stone for future interstellar exploration, If humanity ever develops the technology to travel beyond the solar system, a nearby brown dwarf could be one of our first destinations. But for now, brown dwarfs remain some of the most elusive and intriguing objects in the universe. They challenge our understanding of what it means to be a star, blur the line between planets and stellar remnants, and hint at the existence of unseen populations that could reshape our understanding of the cosmos. As we continue to uncover their secrets, one thing is certain: brown dwarfs are far more than failed stars. They are unique, enigmatic, and full of surprises, reminding us that even in the vastness of space, there are still countless mysteries waiting to be solved. Brown dwarfs are often described as the missing link between planets and stars, but this description barely scratches the surface of their complexity. These objects don't just exist in a gray area of classification. They challenge our very understanding of celestial formation, evolution, and the limits of what a star can be. Unlike fully fledged stars that shine brightly for billions of years, brown dwarfs exist in a state of perpetual cooling, slowly radiating away the heat left over from their formation. This makes them some of the most mysterious objects in the cosmos, hiding in the darkness and waiting to be discovered. One of the greatest challenges in studying brown dwarfs is that they are incredibly difficult to detect. Because they emit very little visible light, most of the brown dwarfs we know about have been found using infrared telescopes, which can pick up the faint glow of their residual heat. Even then, many brown dwarfs remain hidden in the vastness of space, undetectable with our current technology. It's entirely possible that the number of brown dwarfs in our galaxy far exceeds the number of known stars, making them one of the most abundant, yet least understood, celestial objects in the universe. To truly understand brown dwarfs, we have to examine their formation. Like stars, brown dwarfs begin their lives in dense clouds of gas and dust. These clouds collapse under their own gravity, forming protostars, hot, dense objects that continue to pull in material from their surroundings. But for a brown dwarf, something goes wrong in this process. It never gathers enough mass to reach the critical threshold required for hydrogen fusion to begin. Instead of igniting into a star, it remains in a state of arrested development, glowing faintly as it slowly cools over millions or even billions of years. This raises an interesting question. What determines whether a forming object becomes a star or a brown dwarf? The answer lies in mass. Astronomers estimate that an object needs to be at least 75 to 80 times the mass of Jupiter, about 7 to 8% the mass of the Sun, to sustain hydrogen fusion. If an object falls short of this mass, fusion never takes hold, and it becomes a brown dwarf. However, some brown dwarfs may briefly experience a form of fusion. The heaviest brown dwarfs, those near the upper mass limit, can fuse deuterium, a rare isotope of hydrogen, for a short period of time before running out of fuel. But deuterium fusion is much weaker and doesn't last long, meaning these brown dwarfs soon settle into a long period of gradual cooling. This cooling process makes brown dwarfs unique in the cosmic landscape. Unlike stars, which maintain a relatively stable brightness for billions of years, brown dwarfs continuously change in temperature, luminosity, and even atmospheric composition as they age. A newly formed brown dwarf can be incredibly hot, sometimes exceeding 2000 degrees Celsius, but over time, it cools down to temperatures that can be lower than the freezing point of water. Some of the oldest brown dwarfs in the universe may be no warmer than a chilly winter night on Earth. As a brown dwarf cools, its appearance changes drastically. The hottest brown dwarfs have atmospheres rich in hydrogen and helium, similar to small stars, but as they cool, more complex molecules begin to form. Silicate clouds, metal oxides, and even exotic compounds like titanium dioxide can condense in their atmospheres. This process is similar to cloud formation on Earth but on a much more extreme scale. Some brown dwarfs are thought to have iron rain, where molten metal condenses in their upper atmospheres and falls like fiery droplets through their clouds. At even lower temperatures, brown dwarfs begin to resemble gas giant planets like Jupiter and Saturn. Methane becomes a dominant component of their atmospheres, and in the coldest brown dwarfs, water vapor can form thick clouds. This is one of the reasons astronomers study brown dwarfs so intensely. They offer a rare opportunity to observe planetary atmospheres in an environment where they aren't overwhelmed by the glare of a parent star. The study of brown dwarfs has also provided valuable insight into planetary weather systems. Observations have revealed that some brown dwarfs have massive, long-lasting storm systems, similar to Jupiter's Great Red Spot but on an even grander scale. These storms can span thousands of kilometers and persist for years or even decades. Some brown dwarfs also experience extreme variations in brightness, suggesting that their cloud cover is constantly shifting, with violent weather patterns shaping their appearance. Despite their similarities to planets, brown dwarfs differ in one critical way: they don't orbit stars. Most brown dwarfs roam freely through space, unbound to any solar system. These rogue brown dwarfs are of particular interest to astronomers because they offer a glimpse into what our gas giant planets might look like if they were isolated in space. By studying rogue brown dwarfs, scientists can better understand the atmospheres, chemistry, and internal structures of planets beyond our solar system. Another fascinating mystery surrounding brown dwarfs is the possibility that they could host their own planetary systems. In recent years, astronomers have discovered that some brown dwarfs have planets orbiting them, just like stars. This challenges our understanding of planetary formation. Typically, planets are thought to form within the swirling disks of gas and dust surrounding young stars. But if planets can form around brown dwarfs, it suggests that planetary formation might be more flexible than we previously thought. These planetary systems raise another intriguing question: could any of these planets be habitable? The traditional definition of the habitable zone, the region around a star where conditions might allow liquid water to exist, doesn't apply neatly to brown dwarfs. Since brown dwarfs cool over time, their habitable zones shift, moving inward as they lose heat. A planet that starts out in a warm, life-friendly zone may eventually freeze as its brown dwarf dims. However, some scientists have proposed alternative scenarios in which life could persist. If a planet has a thick enough atmosphere, strong greenhouse gases could trap enough heat to keep conditions stable for long periods. Additionally, tidal heating, a process where the gravitational forces from a brown dwarf flex a planet's interior, generating heat, could provide an energy source that keeps a planet warm even as its brown dwarf cools. If life ever existed in a brown dwarf system, it would have to adapt to an incredibly alien environment. Without the steady sunlight of a main sequence star, life forms would need to rely on other sources of energy, such as geothermal heat or chemical reactions. It's possible that life on such planets could be vastly different from anything we know on Earth, thriving in conditions we might consider uninhabitable. As astronomers continue to search for new brown dwarfs, they are also trying to understand just how many of these objects exist. Current estimates suggest that for every star in our galaxy, there may be several brown dwarfs, meaning that they could be one of the most common types of celestial bodies in the universe. If this is true, it would mean that much of the mass of the Milky Way is hidden in these faint, elusive objects, waiting to be uncovered. With new telescopes like the James Webb Space Telescope, scientists are beginning to explore brown dwarfs in greater detail than ever before. These observations could help answer some of the biggest remaining questions. How do brown dwarfs form? How do their atmospheres change over time? Could they have exotic weather patterns unlike anything seen before? And perhaps most intriguingly, could some of them be hiding unseen planets, or even harboring the conditions for life? Brown dwarfs are not just failed stars or oversized planets. They are something entirely unique. They challenge our classifications, blur the boundaries between celestial objects, and reveal just how much we still have to learn about the universe. As we continue to study them, we may find that these mysterious objects hold answers to some of the biggest questions in astrophysics. Brown dwarfs exist in a strange in-between state that defies simple classification. They are not massive enough to sustain hydrogen fusion like a star, yet they are significantly more massive than the largest planets. This unique position in the cosmic hierarchy makes them invaluable for understanding not only stellar evolution but also planetary atmospheres, extreme weather patterns, and even the potential for exotic life in the universe. The more we study them, the more they challenge our assumptions about how celestial bodies form and evolve over time. One of the most intriguing aspects of brown dwarfs is their incredibly diverse temperature range. Unlike stars, which maintain relatively stable internal fusion processes, brown dwarfs cool over time. A newly formed brown dwarf can be as hot as a small star, with surface temperatures reaching thousands of degrees. These young brown dwarfs emit most of their radiation in the infrared spectrum, making them detectable by infrared telescopes. However, as they age, they gradually cool down, and their brightness fades. Some of the coldest brown dwarfs discovered so far, known as white dwarfs, have surface temperatures comparable to a warm summer day on Earth. This cooling process creates a fascinating evolution in atmospheric composition. Young brown dwarfs resemble stars in their appearance, with mostly hydrogen and helium in their atmospheres. However, as they cool, more complex molecules begin to form. The hottest brown dwarfs have clouds made of silicates and iron, while cooler brown dwarfs develop atmospheres rich in methane, ammonia, and water vapor, much like gas giants in our own solar system. The presence of these molecules suggests that studying brown dwarfs can provide insight into exoplanetary atmospheres, particularly for gas giants orbiting other stars. Some brown dwarfs display dramatic changes in brightness over time, which hints at complex atmospheric dynamics. Observations suggest that many brown dwarfs experience massive storm systems, similar to but much more extreme than Jupiter's Great Red Spot. These storms can cause fluctuations in brightness as clouds shift and rotate across their surfaces. Some brown dwarfs have been observed to have storm systems covering significant portions of their surface, which persist for years or even decades. One of the most significant discoveries in recent years is the presence of rogue brown dwarfs, objects that drift freely through space, unbound to any particular star system. These rogue brown dwarfs likely formed in stellar nurseries just like stars but were ejected due to gravitational interactions. Others may have formed in isolation, never accumulating enough mass to become full-fledged stars. The existence of these solitary wanderers raises interesting questions about their potential planetary systems. Could some of these brown dwarfs have planets orbiting them? And if so, what would it be like to live on a planet orbiting a failed star? The idea of planets orbiting brown dwarfs presents an exciting challenge to traditional models of planetary formation. Planets are generally thought to form in the protoplanetary disks that surround young stars. But brown dwarfs, particularly the smallest ones, might not have the same type of accretion disks that stars do. Yet astronomers have discovered planetary mass objects orbiting some brown dwarfs, suggesting that the processes that create planets may be more versatile than we previously thought. One of the biggest mysteries surrounding brown dwarfs is their overall population in the universe. Because they are so faint and difficult to detect, astronomers suspect that we have only found a small fraction of the brown dwarfs that exist in our galaxy. Some estimates suggest that for every star in the Milky Way, there could be several brown dwarfs lurking unseen in the darkness. If this is true, it means that brown dwarfs may account for a significant portion of the galaxy's hidden mass. As we continue to study brown dwarfs, new questions emerge. What is the smallest possible mass for a brown dwarf? Can some brown dwarfs have moons with subsurface oceans, potentially providing habitable environments? Could brown dwarfs play a role in the search for extraterrestrial life by hosting planets in stable orbits? These are just some of the many mysteries that remain unanswered. New telescopes, like the James Webb Space Telescope, are revolutionizing our ability to study brown dwarfs in greater detail. By capturing high-resolution infrared images, astronomers can analyze their atmospheric compositions, track their weather patterns, and even look for potential exoplanets orbiting them. Future missions may uncover even colder and fainter brown dwarfs, pushing the boundaries of what we know about these enigmatic objects. Brown dwarfs blur the lines between planets and stars, challenging our definitions of celestial bodies. They are among the most common yet least understood objects in the cosmos. As our technology advances and our understanding deepens, these mysterious entities may hold the key to unlocking new insights about the formation of planets, the evolution of stellar systems, and the vast, hidden population of objects that roam our galaxy. The more we learn about them, the more we realize just how much remains unknown. This video is for educational or Entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.